We live on a tiny, blue dot suspended in the cosmic dark, a fragile world orbiting an average star, in an unremarkable galaxy, amidst hundreds of billions more. And in all that vastness, in the silence between the stars, a haunting question echoes: where is everybody? With billions of planets, countless chances, and the universal building blocks of life spread throughout the cosmos, we should already have neighbors waving across the stars. Yet, we hear nothing. We see nothing. We are alone, or so it seems. But what if the silence hides something far stranger than absence? What if alien life exists, and we've already brushed against it, but didn't realize it? Or worse, what if something is keeping them away? Across the next 4 hours, we'll dive into the most convincing alien theories, not wild conspiracies or blurry UFO footage, but evidence-based puzzles and cutting-edge scientific enigmas that force us to confront the question: are we truly alone in the universe? But before we continue, subscribe to the channel. Let's begin with the riddle that haunts every scientist searching the stars. The Fermi Paradox. Imagine you're sitting in a crowded room, but somehow, no one speaks. No one makes a sound. You know the room should be full of life, voices, movement. But there's only silence. This is the unsettling feeling at the heart of the Fermi Paradox. First proposed by physicist Enrico Fermi during a lunchtime conversation in 1950, the paradox is deceptively simple. If intelligent alien civilizations are common in the universe, then where are they? Why haven't we heard from them, seen them, or been visited? On the surface, it seems like a question of communication. But dig deeper, and you uncover a gaping contradiction between high scientific probability and absolute observational silence. Let's start with the numbers. The Milky Way alone contains over 100 billion stars, and many of them are billions of years older than our Sun. Based on current estimates, there are likely tens of billions of Earth-like planets in our galaxy, planets in the so-called habitable zone, where temperatures allow liquid water, a key ingredient for life as we know it. Statistically, it would be absurd to assume that Earth is the only planet where life arose. And even more absurd to think it's the only one where intelligent life emerged. Now, consider the timeline. Many stars formed long before ours did, by billions of years. If a civilization had even a million-year head start, their technology could be so advanced as to appear almost magical. They could have explored the galaxy, colonized it, or at least sent self-replicating probes, often referred to as von Neumann probes, to spread throughout the stars. These probes could travel from one system to another, using resources to build copies of themselves and continue the cycle. The calculations suggest that a civilization with this kind of technology could colonize the entire galaxy in a few million years, a blink of an eye on cosmic timescales. And yet, nothing. No probes. No signals. No contact. No evidence of visitations. Nothing at all. So why? What could explain this eerie silence? Many theories have been proposed, each as fascinating and unsettling as the next. One possibility is that we're the first. Maybe Earth was lucky. Maybe conditions here were incredibly rare. According to the rare Earth hypothesis, which we'll discuss later, life itself might be common, but complex. Intelligent life could be exceedingly rare. In this view, while microbes may exist on countless planets, advanced civilizations are an anomaly. Another possibility: they're out there, but hiding. This leads to the zoo hypothesis, which suggests that alien civilizations are deliberately avoiding contact with us, watching from afar, studying us like animals in a preserve. Perhaps we're not ready, ethically or technologically, for contact. Or maybe revealing themselves would disrupt our natural development. There's also the theory of self-destruction. Every civilization that advances far enough inevitably creates the means of its own extinction, through nuclear war, environmental collapse, artificial intelligence, or other catastrophes. This leads us to the chilling idea of the Great Filter, which we'll explore in depth later. It suggests that there's a barrier, some event or series of events, that prevents intelligent life from surviving long enough to make contact. Alternatively, maybe they're already here, in ways we don't recognize. Perhaps alien life is so fundamentally different that we can't detect it, non-biological, non-carbon based, or existing in dimensions or forms we can't perceive. Some scientists have suggested that we're not listening properly. We've only been using radio telescopes for about a century. The signals we send into space are weak and scattered, and the area of the sky we've scanned is microscopic compared to the vastness of space. Imagine searching for a needle in a haystack, when you don't even know what the needle looks like. And what if they're using a technology we haven't invented yet? Something beyond radio, quantum communication, neutrino-based messaging, or something completely alien to us. It would be like expecting to receive a text message on a stone tablet. Then there's the haunting idea that they tried to reach out, but failed. Maybe their messages have long passed us by. Maybe they're buried in cosmic noise, or they were sent before we had the technology to notice. Or maybe they gave up, convinced that no one was listening. Finally, there's the possibility that the universe is hostile to intelligent life. Gamma-ray bursts, supernovae, black holes, and other cosmic disasters might routinely wipe out developing civilizations before they can spread. Life might constantly emerge, only to be erased before it can flourish. In the end, the Fermi Paradox doesn't just ask where aliens are. It forces us to confront the fragility of our own existence. Are we special? Or are we on the edge of a great cosmic graveyard, whispering into a void? The silence isn't just puzzling. It's terrifying. Because maybe the answer isn't that aliens don't exist. Maybe the answer is that they don't last. But just as the silence of the cosmos echoes through the vastness of space, there was one moment, one extraordinary blip in the static, that seemed to defy the silence. A single event that has haunted astronomers and SETI researchers for decades. On August 15, 1977, while scanning the skies for extraterrestrial radio signals using the Big Ear radio telescope in Ohio, astronomer Jerry R. Emmons stumbled upon something anomalous. Something so startling that he circled it on the computer printout and wrote a single, excited word in red pen next to the data. Wow! This wow signal, as it came to be known, was a 72-second-long burst of radio energy at a frequency of 1420.456 MHz, incredibly close to the 1420 MHz hydrogen line. That frequency, associated with the emission from neutral hydrogen, the most abundant element in the universe, has long been considered a logical candidate for interstellar communication. It's a kind of universal calling card, something any intelligent species would likely recognize. What made the signal so compelling was its unmistakable profile. It rose and fell in intensity just as a signal would if a beam from space swept across the Earth, picked up as the telescope rotated. It didn't look like a terrestrial transmission, a satellite bounce, or natural cosmic background. It looked intentional. But despite the excitement and intense follow-up efforts, the wow signal was never detected again. Dozens of telescopes have tried to find it, listening at the same frequency and location in the sky. Nothing. Not a whisper. The original signal seemed to come from the direction of the constellation Sagittarius, near the star group Chi Sagittarii. However, the Big Ear telescope had 2 feed horns, meaning it could have picked up the signal from one of 2 sky locations. The source couldn't be pinpointed with certainty, and the lack of recurrence only deepened the mystery. Natural signals repeat or are explained. Artificial signals, if they're deliberate, should too. There were many theories proposed in the aftermath. Some argued it was a terrestrial interference, or a signal bouncing off space debris. But none of those explanations fully accounted for its frequency, duration, and isolated nature. Others speculated about comet emissions, which was later challenged when the signal couldn't be replicated during comet flybys. To this day, the wow signal remains the best candidate for a deliberately transmitted alien radio signal. But it's a ghost, a message without a messenger, a flare with no follow-up. There's something deeply haunting about that. The idea that somewhere, perhaps light years away, a civilization may have aimed a transmission at us, a greeting, a probe, a test, and we were there to catch it. But only once. Did they give up after that? Did we miss our window? Or worse, Was that their final cry before vanishing into cosmic silence? It's moments like the wow signal that ignite the imaginations of both scientists and dreamers. It wasn't proof. But it wasn't random either. It was just enough to suggest we're not alone, and just vague enough to deny us certainty. This is the agony and wonder of SETI. The stars may be quiet, but now and then, something whispers back. And then, from the vast interstellar dark, something entered our solar system, something we had never seen before. In October of 2017, astronomers in Hawaii detected a strange object passing through space at incredible speed. It was given the name Oumuamua, which in Hawaiian means a messenger from afar arriving first. And that name, perhaps unintentionally, captured the imagination of the world. Because this object wasn't just unusual, it behaved like nothing else we had ever observed. At first glance, it was identified as a comet or asteroid. But very quickly, that explanation began to unravel. For one, its trajectory was hyperbolic, meaning it wasn't bound by the gravity of our Sun. It came from outside the solar system, from another star system entirely, making it the first known interstellar object to pass through our cosmic neighborhood. But even more puzzling was its shape and motion. Based on how it reflected sunlight, scientists estimated that Oumuamua was highly elongated, perhaps 10 times longer than it was wide, something like a cigar or pancake, depending on how it tumbled. No known natural asteroid or comet had ever displayed such proportions. It was tumbling end over end, not just spinning, suggesting it wasn't a gravitationally relaxed body like most objects in space. And then came the real mystery. As it left the solar system, Oumuamua accelerated, ever so slightly, but measurably, without any visible cause. Normally, comets speed up when sunlight causes their icy surfaces to sublimate, creating jets of gas that push them forward. But Oumuamua showed no signs of outgassing. No tail. No emissions. No dust. Nothing that would explain the thrust. Yet it changed speed, just as if it were being propelled, or steering. This anomalous acceleration prompted scientists like Harvard astronomer Avi Loeb to suggest a radical possibility. What if Oumuamua wasn't natural? What if it was an alien probe, a piece of interstellar technology, perhaps damaged, abandoned, or sent deliberately to observe planetary systems like ours? Loeb argued that its thin, flat shape might even be consistent with a light sail, a spacecraft that uses radiation pressure from starlight to travel immense distances. If such technology existed, it could cross galaxies without using fuel, pushed gently but continuously by photons. An idea long theorized by humans, but never realized. Could another civilization have built one? The scientific community was split. Some dismissed the idea as science fiction, an overreach from limited data. Others countered that dismissing such a possibility too quickly was unscientific in itself. After all, the hallmark of science is to consider all plausible explanations, especially when natural ones fall short. Alternative theories proposed that Oumuamua might be a fragment of a disrupted planetary body, or even a hydrogen iceberg slowly releasing invisible gas. But those hypotheses had problems too. Such materials should have evaporated before reaching US or weren't stable enough to exist in deep space for millions of years. What made the encounter even more frustrating is that we discovered Oumuamua too late. By the time we realized how bizarre it was already racing away from Earth at over 315,000 kilometers per hour. Too fast and too distant for any spacecraft to catch it. We had no chance to redirect a probe. No opportunity to inspect it up close. It came, it puzzled, and it was gone. And unlike the wow signal, which was purely a momentary auditory mystery, Oumuamua was a physical intruder, a tangible traveler from beyond. But it left no answers, only theories, only haunting possibilities. If it was alien technology, was it active? Abandoned? Was it collecting data? Was it broken? Was it the debris of a civilization long dead, drifting through the stars like a message in a bottle? Or was it, in the end, just an improbably weird rock? The truth remains out of reach. But its existence alone proves that objects from other star systems can and do pass through ours. And next time, we might be ready. New telescopes, like the Vera C. Rubin Observatory, aim to catch the next visitor earlier, perhaps early enough to study it in real time, or even launch a mission to meet it. For now, Oumuamua remains one of the strangest, most compelling riddles in modern astronomy. A silent, spinning enigma that came from the stars, and vanished back into them. Just when we thought the universe had already thrown its strangest signals at us, a new kind of cosmic whisper emerged, briefer than a blink, yet packing more energy than our sun emits in days. In 2007, while reviewing archival data from the Parkes Observatory in Australia, astronomer Duncan Lorimer and his students stumbled upon a signal that defied expectations. It was powerful, sharp, and lasted just a few milliseconds. It came to be known as the Lorimer burst, and it was the first fast radio burst, or FRB, ever recorded. At first, scientists were skeptical. It could have been a glitch, interference, or an oddball phenomenon. But over the next decade, dozens more FRBs were discovered, and then hundreds. These weren't isolated errors. They were real, and they were coming from deep space, from galaxies billions of light years away. Fast radio bursts are incredibly brief pulses of radio waves, often lasting just a few thousandths of a second. But in that fleeting instant, they emit more energy than 500 million suns. What's even more bewildering is their randomness. Many are one-off events, appearing once, then never again. Others are repeaters, blinking out signals sporadically or, in rare cases, on a regular schedule. Their origin? Still a complete mystery. Some FRBs originate from star-forming regions, others from the outskirts of galaxies. They don't seem to obey a universal pattern. What causes them? Natural theories abound. Some point to magnet-stars, highly magnetized neutron stars, as culprits. The idea is that a violent magnetic quake or collision could release a sudden, massive burst of radio energy. Others speculate about black hole neutron star mergers, or cosmic strings, or even supernovae. But not all FRBs fit neatly into those models. Some repeat, and some do so with periodic precision. One FRB, named FRB 180916, emits bursts every 16.35 days, like clockwork. That kind of regularity is highly unusual in nature, and it reignited interest in artificial origins. Could these be intentional signals? Some scientists and SETI researchers have dared to ask, what if FRBs are alien beacons? Or energy sources used to power a spacecraft? After all, a civilization with advanced technology could harness astronomical amounts of energy, and an intense burst of radio waves might be a byproduct, or even a deliberate form of communication across the stars. A particularly provocative hypothesis comes from a 2017 paper co-authored by Avi Loeb, the same astronomer who raised eyebrows with his interpretation of Oumuamua. He suggested that FRBs could be artificial beams, possibly used to propel light sails for interstellar travel. Imagine a powerful radio wave used to push a thin spacecraft, riding on a laser wind across galaxies. If we happen to be in the path of such a beam, it might appear to us as a sudden, unexplained FRB. But why would such signals be so brief? Perhaps they're not meant for us at all. We're simply in the crossfire, catching the echo of civilizations doing something extraordinary with energy on a scale we can barely imagine. The challenge in unraveling the mystery of FRBs is their unpredictability. They appear without warning, from random locations, and vanish just as fast. But technology is catching up. Instruments like the CHIME radio telescope in Canada and upcoming projects like the Square Kilometre Array are designed to detect thousands of FRBs per year. And each new detection adds a piece to the puzzle. Still, there's a chilling aspect to FRBs. If they are artificial, what kind of civilization is creating them? According to the Kardashev scale, which we'll discuss later, a civilization capable of emitting such energy intentionally might be far beyond our level of development. Maybe a Type 2 or Type 3 civilization, harvesting power from stars or entire galaxies. It's also possible we're witnessing ancient signals, launched millions or billions of years ago, only now reaching us. Are they still alive? Are they watching for a reply? In the end, FRBs remind us of something profound, that we are constantly bombarded by signals from the deep cosmos. We don't yet know if they're nature's fireworks or someone else's transmissions. But they are out there, fast, powerful, and unignorable. They could be natural. They could be engineered. But either way, they challenge our understanding of the universe, and hint at possibilities far beyond our current grasp. While strange signals and fleeting cosmic visitors ignite speculation, there's another line of evidence that steadily builds a stronger case, not through anomaly, but through abundance. It's in the planets themselves. Over the past few decades, our understanding of the universe has undergone a profound shift. What was once a guess, a theory, a hope that other worlds existed, has become a flood of discovery. And among these worlds, some occupy a zone that could make all the difference. A place that is not too hot, not too cold, but just right for life. This is the so-called habitable zone, often referred to as the Goldilocks zone. It's the region around a star where conditions could allow liquid water to exist on a planet's surface, not frozen into glaciers, nor boiled away by heat. Since life on Earth depends so heavily on water, this zone has become a prime target in the search for extraterrestrial life. In 1992, the first exoplanets, planets orbiting stars beyond our Sun, were discovered around a pulsar. But it wasn't until 1995 that scientists found a planet orbiting a normal, Sun-like star. From that point on, the floodgates opened. With the launch of NASA's Kepler Space Telescope in 2009, thousands of exoplanets began to emerge from the data. As of now, over 5,000 confirmed exoplanets have been discovered, with thousands more candidates awaiting verification. They come in all sizes, compositions, and orbital arrangements: gas giants larger than Jupiter hugging their stars in infernal proximity, rocky super-Earths orbiting cool red dwarfs, and strange planets with lava oceans, silicate rain, or permanent nights. But among them, hundreds have been found within the habitable zones of their stars. Some orbit stars similar to our own, others revolve around red dwarfs, which are smaller, cooler, and far more common than Sun-like stars. In fact, the nearest potentially habitable exoplanet, Proxima Centauri b, orbits the star closest to us, just 4.2 light-years away. These planets are not just statistical curiosities. They tell us something profound: our solar system is not unique. Earth is not the only world with the potential for life-supporting conditions. And life, if it arises wherever the conditions are right, could be spread throughout the galaxy. The diversity of these planets is staggering. Some are super-Earths, rocky planets up to 10 times the mass of Earth, with thick atmospheres and strong gravity. Others are ocean worlds, possibly covered in global seas miles deep. There are planets in binary systems, where two suns rise and fall. There are rogue planets, ejected from their systems, drifting through the galaxy in eternal night, possibly warmed by internal heat. And even more fascinating is the realization that the habitable zone is not static. It changes depending on the star's temperature and age. A red dwarf's habitable zone is much closer to the star, making planets there vulnerable to flares and radiation. But it also means those stars can live for trillions of years, offering enormous timescales for life to develop and evolve. Many of the exoplanets found in habitable zones are still too far to study in detail. But that's changing. With new telescopes like the James Webb Space Telescope, JWST, and future missions like LUVOIR and HABEX, we are beginning to peer into their atmospheres, to analyze their chemical compositions, and to look for biosignatures, gases like oxygen, methane, or even industrial pollutants that could suggest biological or technological activity. The existence of these potentially habitable exoplanets doesn't prove alien life exists. But it shifts the conversation. It makes the idea no longer speculative but statistical. With billions of such planets likely existing in our galaxy alone, the odds of Earth being the only cradle of life seem vanishingly small. And if life does exist on these distant worlds, whether microbial or intelligent, it could take forms we've never imagined. It might thrive under purple skies, swim in ammonia oceans, or breathe in carbon dioxide like oxygen. But the key is that the conditions are there. The universe is building the right ingredients over and over again. Every new planet found in the habitable zone is a potential new home. A possible mirror to Earth, or perhaps a cautionary tale. A place where life could flourish, or fail. But either way, they tell us something we cannot ignore. We are not the center of the universe. We are just one node in a vast, living web of potential worlds. And out there, in the twilight between heat and cold, some of those worlds may already be alive, waiting for the day when someone finally hears their signal, or arrives. Among all the systems we've discovered beyond our own, few have stirred as much excitement, or as many questions, as a small, dim star just under 40 light-years away. It's a star so faint it can't be seen with the naked eye, and yet what orbits it has captivated scientists, dreamers, and alien theorists alike. It's called TRAPPIST-1, and what makes it remarkable is not just that it has planets, but how many, how Earth-like, and how tightly packed they are. In 2017, NASA announced something extraordinary. The TRAPPIST-1 system contains 7 Earth-sized rocky planets orbiting an ultra-cool dwarf star, and at least 3 of them reside within the star's habitable zone. That's not 1, not 2, but 3 planets where conditions could, in theory, support liquid water, and perhaps life. What makes this discovery so compelling isn't just the number, but the arrangement. These planets are all closer to their star than Mercury is to the Sun, forming a compact family of worlds, each tugging on the others gravitationally. This proximity means they complete their orbits in just a few days, and their configurations create regular eclipses, an astronomer's dream, because these transits allow us to study their sizes, densities, and atmospheres with exceptional precision. The star at the heart of this system, TRAPPIST-1, is much smaller and cooler than our Sun. It emits a faint red glow, and will burn for trillions of years, offering any potential life forms an astonishingly long time to evolve. The lower energy output means its habitable zone is much closer in, and the planets there are tidally locked, one side always facing the star, the other in eternal night. This raises fascinating possibilities. Could alien life exist in the narrow twilight zone, the band between day and night, where temperatures are just right? Could atmospheric circulation distribute heat well enough to make the planets more uniformly habitable? Current models suggest that yes, it's possible. Some TRAPPIST-1 planets may have thick atmospheres, which could moderate climate extremes and support surface liquid water. What's especially promising is that these planets are terrestrial, meaning they're rocky, not gas giants like Jupiter or Neptune. This puts them among the best exoplanet candidates for future atmospheric study. Telescopes like James Webb are already focusing on TRAPPIST-1, analyzing light that passes through the planet's atmospheres as they transit their star. From this, scientists hope to detect biosignature gases, oxygen, ozone, methane, or even carbon dioxide, in quantities that suggest life-related processes. And because the star is so close to Earth in cosmic terms, we may soon have detailed readings of the atmospheric composition of multiple Earth-sized worlds. In the coming years, the TRAPPIST-1 system may become our first close look at truly Earth-like planets beyond our solar system, not in imagination, not in science fiction, but in real, observable data. Now imagine, for a moment, the implications. 7 planets, Earth-sized, orbiting a single star. 3 potentially habitable. If life arose on one, could it spread to the others? Could microbial life have hitched a ride on rocks ejected by impacts and colonized neighboring planets, just as some versions of the panspermia theory suggest? Or if intelligent life developed, would it see itself not as a species tied to one planet, but as inheritors of an entire system? Imagine a civilization born among 7 siblings, with night skies dominated not by distant stars, but by nearby Earth-like worlds, close enough to reach in weeks or months with the right propulsion. Such a civilization wouldn't think of interplanetary travel as distant or theoretical. It would be a fact of life, perhaps even a foundational element of their culture and biology. They would evolve with awareness of other worlds, possibly even exchanging life, technology, or languages between them. Of course, there's no evidence yet of intelligent life in TRAPPIST-1. But the odds are intriguing. This single, faint star system represents a miniature galaxy of opportunity. And its very existence forces us to reconsider just how common life-sustaining systems might be. We used to think the solar system was special. But TRAPPIST-1 shows us that compact systems with rocky planets are not only possible. They might be common, especially around red dwarf stars, which make up about 70% of the stars in the galaxy. It's no longer a question of whether Earth-like planets exist. It's now a question of how many are out there, and how many are already alive. As we scan the heavens and discover thousands of distant worlds, our attention shifts from simply finding planets to answering a far deeper question: are they alive? But detecting life on a distant exoplanet is not as straightforward as spotting a tree or a microbe through a telescope. The planets are too far, too faint, their surfaces shrouded by the glare of their stars. So instead, we search for what life leaves behind, its fingerprints in the air. This is the cutting edge of the search for extraterrestrial life, the hunt for biosignature gases in alien atmospheres. A biosignature gas is any gas in a planet's atmosphere that is produced, or heavily influenced, by biological activity. On Earth, life has profoundly altered the composition of our atmosphere. Oxygen, for example, is extraordinarily reactive and wouldn't persist in large quantities unless it was constantly replenished, primarily by photosynthesis. Methane is another key biosignature, produced by a variety of microbes and biological processes. The presence of these gases, particularly in combination, could be a strong indicator that a planet is not just habitable, but inhabited. With next-generation telescopes now coming online, like the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope, we can begin the delicate work of reading the spectral fingerprints of exoplanet atmospheres. When a planet passes in front of its star, a tiny fraction of starlight filters through its atmosphere. By analyzing how this light is absorbed at different wavelengths, scientists can determine what gases are present. And this is where the science becomes both thrilling and subtle. A single biosignature gas like oxygen isn't enough, because there are abiotic, non-biological, ways to produce it. For instance, ultraviolet radiation from a star can break apart water vapor or carbon dioxide and generate oxygen. Methane, too, can be created through geological processes like volcanic activity or serpentinization. But when you see oxygen and methane together, that's different. These gases tend to react with each other. On Earth, their coexistence requires constant renewal by biological sources. Finding that same imbalance elsewhere could hint at a similar dynamic, possibly microbial life exhaling gases into the sky of another world. Then there are more exotic biosignatures, depending on the type of life and environment. Nitrous oxide, for instance, is a byproduct of soil microbes. Chloromethane can be released by certain plants. Even dimethyl sulfide, a compound associated with plankton, might one day be detected. And beyond Earth-like biochemistry, we may find signatures we haven't yet imagined, products of life based on silicon, ammonia, or other alien chemistries. The choice of target planets is critical. We prioritize Earth-sized planets in the habitable zones of their stars, ideally orbiting quiet, dim red dwarfs where the signal-to-noise ratio is more favorable. Systems like TRAPPIST-1 and LHS 1140 are high on the list. The JWST is already beginning to collect early spectra from such worlds, and the data is promising. But the interpretation remains delicate. For example, a planet might have a thick hydrogen-dominated atmosphere that hides biosignatures. Or a world could be covered in haze or clouds, blocking our ability to see into the lower atmosphere. And even when we detect a signal, it can take years of observations to confirm and rule out false positives. Still, the progress is remarkable. In the early 2000s, detecting an exoplanet was revolutionary. Today, we are studying their air, sniffing distant worlds, atom by atom, from across the void. And the implications are staggering. Suppose one day we detect a planet with an oxygen-methane disequilibrium, orbiting a quiet star, showing no signs of intense radiation or geological trickery to explain it. Suppose its temperature is stable, its size Earth-like, its orbit within the habitable zone. Suppose everything points to the same conclusion: this planet is breathing. Would that be definitive proof of life? Perhaps not. But it would be a cosmic alarm bell, a target for follow-up missions, investment, debate, and philosophical reflection. It would force us to confront, more seriously than ever, the possibility that life is not unique to Earth. And even more importantly, it would suggest that life finds a way. Given the right conditions, the right chemistry, and the right spark, biology emerges to shape its world. We are on the verge of moving from planetary discovery to planetary diagnosis, reading the chemical signatures of life from light years away. One day, maybe soon, the data will reveal not just a distant world, but a living one. Not all alien mysteries lie light years away in the far reaches of the galaxy. Some linger much closer, just one planet over. In September 2020, a scientific bombshell dropped. Researchers had detected phosphine gas in the upper atmosphere of Venus, a molecule that, on Earth, is almost exclusively produced by microbial life or through industrial means. This unexpected discovery thrust Venus, long considered one of the most inhospitable planets in the solar system, into the spotlight of astrobiology. Phosphine is a toxic, smelly gas with a notoriously nasty reputation. On Earth, it's found in swamps, sludge, and the intestines of certain animals, anywhere anaerobic microbes thrive. It's also used in industry, and doesn't hang around long in our atmosphere unless it's being constantly replenished. Its detection on Venus, where temperatures soar above 460 degrees Celsius and pressures are crushing near the surface, was not just surprising, it was perplexing. The phosphine was detected using the James Clerk Maxwell Telescope in Hawaii and later confirmed by the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile. It appeared to be present in the cloud deck of Venus, roughly 50 to 60 kilometers above the surface, an area that, oddly enough, has temperatures and pressures somewhat similar to Earth's lower atmosphere. While still acidic and hostile, it's the most Earth-like region of Venus, and has long been speculated as a possible niche for aerial microbial life. But here's the twist. There's no known abiotic way to produce phosphine on Venus in the quantities observed. Scientists explored all known non-biological sources: volcanic activity, lightning, chemical reactions in the atmosphere, photochemistry, and even the possibility of minerals catalyzing reactions on airborne dust particles. Every proposed explanation came up short. The production rates were too low or the conditions too implausible. So naturally, attention turned to the biological hypothesis. Could some form of microbial life, possibly floating in the clouds of Venus, be producing phosphine as a metabolic byproduct? This idea, while speculative, isn't new. It dates back to the 1960s, when Carl Sagan and Harold Morowitz suggested that Venus's upper clouds could host extremophiles, microorganisms adapted to harsh conditions. Earth has life that thrives in boiling acid pools and radioactive environments. Why not Venus? The challenge, of course, is that Venus's clouds are made of sulfuric acid, an extremely corrosive substance. For life to survive there, it would need incredibly robust cellular structures, perhaps based on completely alien biochemistry. Alternatively, there might be microenvironments within cloud droplets that are less acidic, or microbial life might be protected inside particulates or biofilms. Despite the excitement, the phosphine detection has not gone unchallenged. Some scientists argue that the signal might have been a false positive, a misinterpretation of spectral data, or even a calibration error. Reanalyses of the data have yielded mixed results, some confirming the detection, others casting doubt. In short, the jury is still out, and the debate continues to rage in scientific circles. But regardless of the outcome, the phosphine episode has done something important. It reopened the case for Venus. For decades, planetary exploration focused almost exclusively on Mars, while Venus was written off as a hellish wasteland. But now, space agencies are returning their gaze. NASA and ESA have greenlit missions to Venus in the coming decade, including Veritas and Da Vinci Plus, which will study the planet's surface and atmosphere in detail. Other concepts involve high-altitude balloons or robotic probes that could float in the clouds and directly sample the environment. If phosphine is confirmed, and if no abiotic source can be identified, it would be one of the most compelling biosignatures ever found, and on a planet that we've long overlooked. It would suggest that life may not require perfect Earth-like conditions. It might arise even in acidic clouds on a world that once had oceans but became a furnace. And that raises a more profound implication. If life can exist on Venus, what does that say about its prevalence across the universe? If even the second planet from the Sun, blistering, acidic, and long thought dead, might host microbial life, then life could be far more resilient, adaptable, and widespread than we ever imagined. Venus, the morning star, may not just be a burning rock in the sky. It might be a reminder that life doesn't always bloom in comfort. Sometimes, it clings to existence in the most unexpected corners of the cosmos. If there's one thing Earth has taught us, it's that life is astonishingly tenacious. For decades, we assumed that life required narrow, stable conditions, mild temperatures, clean water, gentle sunlight, and oxygen-rich air. That assumption was based on our human experience, our comfort zone. But the more we looked, the more we realized that life doesn't just tolerate extremes, it thrives in them. And this realization doesn't just change how we see Earth. It reshapes how we search for life across the cosmos. Enter the world of extremophiles, organisms that inhabit the most hostile, improbable environments on Earth. These creatures are not mere survivors, they are masters of adaptation, living where life was once thought impossible. Their discovery has dramatically widened the scope of where we now believe life could exist, both on Earth and on distant planets and moons. Let's start with the deep ocean. Far below the reach of sunlight, at the bottom of the Pacific and Atlantic, lies a hell's cape of crushing pressure and total darkness. Yet here, around hydrothermal vents, entire ecosystems flourish. These vents spew superheated water, rich in minerals, and create chemical gradients that bacteria exploit in a process called chemosynthesis. Unlike photosynthesis, which depends on light, chemosynthesis uses chemicals like hydrogen sulfide to create energy. These bacteria form the base of a food chain that includes giant tube worms, blind shrimp, and crabs with no pigmentation. This discovery shattered the long-held belief that sunlight was essential for life. It showed us that life can feed on the Earth's inner fire, not just its star. Then there are the acid lovers, organisms that thrive in environments so acidic they would destroy human skin in seconds. In places like Rio Tinto in Spain, where the water is blood red from iron and sulfur compounds, microbes have adapted to pH levels below 1. Similar extremophiles have been found in the Dallol hydrothermal fields in Ethiopia, where acid, heat, and salt create a toxic stew. Some scientists argue that even Dallol is too harsh for life, yet others have identified microscopic survivors clinging to salt formations. In the other extreme, consider Antarctica. Beneath the miles-thick ice of Lake Vostok and Lake Whillans, isolated from the surface for millions of years, microbial life has been found in subglacial lakes. These organisms live in frigid darkness, drawing energy from the slow chemical reactions between rock and water. And it doesn't stop there. Microbes have been discovered living within the ice itself, in the stratosphere, and even inside rocks in Earth's driest desert, the Atacama. Then there are the heat lovers, thermophiles and hyperthermophiles. These microbes thrive in boiling hot springs like those found in Yellowstone National Park, or inside geysers and volcanic vents. Temperatures of 90 to 120 degrees Celsius don't kill them, they support their metabolism. Some even survive autoclave conditions, the same environment used to sterilize surgical instruments. Even in places bombarded with radiation, life persists. The bacterium Deinococcus radiodurans, nicknamed Conan the bacterium, can survive doses of radiation thousands of times higher than what would kill a human. It can also tolerate dehydration, high salt levels, and cold. How? By having extraordinary DNA repair mechanisms and protective proteins that shield its genetic material. We've also found organisms that endure extreme salinity, like those in the Dead Sea and salt flats of Bolivia. Others survive desiccation, lying dormant for years without water and springing back to life when rehydrated. There are even microbes that can be revived after being frozen in permafrost for over 30,000 years. And if that's not enough, some life forms have even survived space itself. In experiments aboard the International Space Station, tardigrades, tiny, water-dwelling animals also known as water bears, were exposed to the vacuum of space, radiation, and temperature extremes. They survived. Some returned to Earth, reproduced, and went on as if nothing had happened. Their resilience has made them a poster child for the possibility of life hitchhiking between planets on meteoroids, a core tenet of the panspermia hypothesis. What do all these examples teach us? They teach us that life is not fragile, it's adaptable. Life doesn't require perfect conditions. It just needs a crack, a niche, a tiny foothold, and it can hold on. It teaches us that what we once considered habitable is a narrow view, a bias shaped by our biology. In truth, the universe may be brimming with places where life could thrive, even if we wouldn't recognize them at first glance. Take Mars, for example. Dry, dusty, and cold on the surface, but potentially harboring salty subglacial lakes or geothermal hotspots underground. Could extremophiles like those on Earth exist there, lying dormant for millions of years and awakening when conditions are right? Or Europa and Enceladus, the icy moons of Jupiter and Saturn. Both have subsurface oceans, heated by tidal forces and possibly rich in hydrothermal activity. If life can thrive at hydrothermal vents in Earth's oceans, why not there? Even Titan, with its lakes of methane and ethane, could support exotic forms of life. It would be very different from Earth-based life, likely operating on a completely alien biochemistry, but the point is that it's possible. And perhaps most tantalizing of all, if Earth's extremophiles can endure freezing, boiling, acidic, radioactive, high-pressure environments, could they survive space travel? Could they, riding inside rocks blasted from planetary impacts, travel between worlds? The concept is no longer fantasy, it's experimental science. So when we look to the stars and wonder about alien life, we must remember, it might not look like us. It might not think like us. It might not need oxygen or sunlight. But if it's out there, it's probably surviving in ways we've only begun to understand. The deep oceans, the volcanic springs, the acid pools, the polar ice caps, the radiation-blasted deserts, they are all telling us the same story. Life is not a miracle. It is a force. And when we finally detect it beyond Earth, it might not surprise us in how it exists, only in how long it took us to find it. As we continue our search for extraterrestrial life, we realize there may be another kind of signal to watch for, one that doesn't emerge from biology, but from civilization. While biosignatures suggest the presence of life, technosignatures hint at something far more profound: intelligent life, capable of shaping its environment, generating energy, and leaving detectable traces in the cosmos. Technosignatures are, in essence, indicators of technology that can be observed at astronomical distances. They're not messages intentionally sent to us, though they could be, but rather the byproducts of intelligent activity: artificial light, radio waves, pollutants, satellites, thermal emissions, or megastructures so vast they bend starlight. The concept radically expands the scope of our search. Instead of waiting for aliens to wave hello with a perfectly tuned radio signal, we now look for the side effects of their existence. Just as someone flying over Earth could infer human presence from city lights, satellites, or atmospheric smog, we hope to detect similar signs from distant worlds. Let's begin with something simple but powerful: light pollution. Artificial lighting on a planet's night side could be visible to advanced telescopes, especially on planets that orbit closely to their stars and rotate slowly, keeping one side in perpetual night. Astronomers theorize that the spectrum of artificial light, particularly LEDs or sodium lamps, could be distinguished from natural reflected starlight. If we ever detect such illumination on a planetary body, especially one otherwise shrouded in darkness, it could be a compelling technosignature. Then there's radio leakage, unintentional broadcasts from TV, radar, or communications networks. Earth has been leaking radio waves into space for about a century. A sufficiently sensitive alien receiver could, in theory, detect these signals. Conversely, if we detect persistent, narrowband radio emissions from a distant star system, particularly if they are not naturally occurring frequencies, it could suggest technological activity. One historical example was the search for signals from Tabby's star, a distant sun-like star that exhibited strange and erratic dimming. While the leading theories point to dust clouds or cometary debris, some speculated the dimming might be caused by an alien megastructure, such as a Dyson swarm, a vast collection of satellites or mirrors harvesting a star's energy. Though no technosignature was found, the incident demonstrated how such anomalies trigger renewed interest in artificial explanations. Another avenue of exploration is pollution. On Earth, human industry has filled the atmosphere with CFCs, chlorofluorocarbons, and other synthetic molecules not known to form naturally. These compounds persist and can absorb infrared radiation in distinct patterns. Detecting similar molecules in the atmosphere of an exoplanet, especially ones that can't be explained geologically or biologically, might point to industrial activity. In fact, researchers are now using telescopes like JWST to begin searching for such gases in exoplanet atmospheres. It's still early, and the signals are faint, but the technology is improving. In time, we may find a planet that reeks of manufacturing, long after the civilization itself is gone. A more speculative but fascinating technosignature involves orbital satellites and megastructures. Just as Earth is now orbited by thousands of satellites, an alien world might be surrounded by a dense halo of technology, what some call a Clark belt. If enough satellites accumulate, they could scatter or block starlight in observable ways. We might detect irregularities in the way a planet transits its star, or notice unusual fluctuations in brightness. And let's not forget heat. Every civilization that uses energy must release waste heat, in accordance with the laws of thermodynamics. If a civilization operates on a truly massive scale, say, Type 1 or 2 on the Kardashev scale, it may emit detectable levels of mid-infrared radiation, a technosignature proposed by several astrophysicists. We can scan galaxies for such excess heat, looking for outliers, galactic regions that radiate too much, without a corresponding increase in starlight. Even gravitational anomalies might signal alien infrastructure. If artificial masses like orbital rings, massive arrays, or shipyards are in place, they could subtly distort the motion of nearby bodies. In the future, precise measurements of planetary wobble, star motion, or stellar occultation could reveal hidden artificial structures. Of course, detecting these signs is hard. It requires careful, patient observation and a deep understanding of natural astrophysical processes. But it also demands openness to the unexpected. The great challenge of technosignature research is not only finding something, it's knowing when what we find cannot be explained by nature alone. SETI, which for decades focused mainly on radio signals, is now expanding to include technosignature detection across multiple wavelengths and disciplines. There's a growing consensus that life may be common, but intelligence may be rare, and technosignatures might be our best bet at confirming it. There's also a sobering angle. Some technosignatures might not be active. We might detect ghosts of civilizations long gone, abandoned cities emitting no light, orbiting debris circling a dead world, or atmospheric pollutants persisting centuries after extinction. In these cases, we wouldn't be discovering living beings, but histories, the echoes of distant, vanished peoples. But even that would be monumental. It would mean we're not the first to build, to dream, to reach for the stars. It would validate our own trajectory and perhaps offer warnings about our future. Technosignatures are the cosmic equivalent of archaeology, except instead of digging through ruins, we sift through light, radiation, and data. We look not for bones, but beacons. Not for cities, but civilizations shadow-etched into the sky. And with every improvement in our instruments and methods, we get closer to being able to detect them, if they exist. Because if intelligence has emerged elsewhere, it may have done what we are doing right now, broadcasting, building, burning, orbiting, reaching. And somewhere in the faint noise of the stars, that footprint may still remain. While technosignatures offer us the scattered footprints of potential intelligence, there's another approach, one far more direct and deliberate. It's the scientific discipline that dares to ask the question most others long avoided: what if someone out there is trying to speak to us? This is the mission of SETI, The search for extraterrestrial intelligence, a vast, ongoing effort to scan the cosmos for signals that suggest intelligence, sent across the unimaginable reaches of space. SETI isn't a single project or organization. It's a global scientific endeavor, spanning observatories, universities, research institutions, and even private initiatives. Its goal is elegant in its simplicity: to detect signals, typically radio waves, that are narrow-band, non-random, and artificial in origin. These signals wouldn't resemble natural cosmic emissions like those from pulsars or quasars. Instead, they'd be tightly focused, repetitive, or mathematically structured, like a whisper through the void. The origin of SETI dates back to 1960, when astronomer Frank Drake launched Project Ozma, the first modern SETI experiment. Using a radio telescope in Green Bank, West Virginia, he pointed the dish toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, listening for any signs of intelligent radio transmission. Though the search came up empty, it ignited a movement. Soon after, Drake developed what is now known as the Drake equation, a probabilistic formula to estimate the number of detectable civilizations in the galaxy. Though its variables are speculative, it offered a framework for thinking about life and intelligence on a cosmic scale. Modern SETI uses massive radio telescopes like the Green Bank Telescope in the US, the Arecibo Observatory, before its collapse, the Allen Telescope Array in California, and Meerkat in South Africa. These instruments can monitor millions of frequency channels simultaneously, scanning vast portions of the sky with ever-increasing sensitivity. And they're not limited to targeted searches anymore. Today's SETI strategies include all-sky surveys, narrowband searches, pulse signal detection, and even efforts to find optical signals, like flashes from high-powered lasers aimed at Earth. One of the most ambitious projects in recent memory is the Breakthrough Listen initiative, launched in 2015 with $100 million in funding from investor Yuri Milner. It's the largest SETI program in history, dedicating significant telescope time to scan millions of stars, dozens of galaxies, and hundreds of frequency bands. Its computational power is staggering, and its data is made available to the public for analysis, opening the search to citizen scientists and AI-based methods. Breakthrough Listen's scale is unprecedented. Instead of scanning a few hundred stars like early SETI projects, it is actively cataloging over 1 million, including those in the Milky Way's galactic plane, nearby clusters, and even stars with known exoplanets in the habitable zone. Its telescopes can detect a radio transmitter with the power of Earth's airport radar from tens of light years away. In other words, if anyone is shouting, we'll hear it. But perhaps what makes SETI so fascinating is not just its technology, but the philosophy behind it. SETI assumes that if intelligent life exists, and if it has developed technology even slightly ahead of our own, then it may also have an interest in communication, discovery, or self-preservation. Civilizations might send out beacons, either to announce themselves or to join a larger galactic network. Or they might be completely unaware of us, and we're merely overhearing their internal communications. The kind of signal SETI searches for would likely be narrowband, centered around a specific frequency. One popular choice is the hydrogen line, a frequency of 1420.405 MHz, associated with the emission of neutral hydrogen atoms. Hydrogen is the most abundant element in the universe, making this an ideal cosmic calling card for communication. It's a kind of universal baseline, chosen because it would likely be familiar to any civilization with knowledge of physics and chemistry. And yet, despite decades of scanning, we have found no confirmed alien signals. There have been intriguing moments like the famous "Wow" signal in 1977, an intense, one-time radio burst that matched the profile of an artificial transmission, but was never observed again. There have been spikes, blips, and anomalies, but none that passed the rigorous scrutiny of replication and analysis. Does this mean SETI has failed? Not at all. The truth is, we've barely scratched the surface. The universe is vast, and our search has been limited to small regions, narrow bands, and short time windows. It's like dipping a cup into the ocean and concluding there are no fish. SETI's challenge isn't just the weakness of the signal, it's the scale of the silence. And there's another wrinkle. Maybe we're looking the wrong way. What if aliens use communication methods beyond radio? What if they use quantum entanglement, neutrino beams, or gravitational waves? What if their messages are encoded in mathematics, delayed by design, or hidden in plain sight, waiting for a civilization advanced enough to notice? These possibilities have prompted SETI researchers to explore a broader range of hypothetical communication methods, while also keeping the traditional radio channels open. And as artificial intelligence becomes more advanced, SETI has begun incorporating machine learning algorithms to analyze the enormous volumes of data, millions of signals, cross-referenced across time and frequency, searching for patterns we might otherwise miss. SETI research also raises deep ethical and philosophical questions. What should we do if we do receive a message? Should we respond? What would we say? Who speaks for Earth? These are no longer just science fiction musings. They are now the subject of active policy discussions, with frameworks proposed for international cooperation and message crafting. Organizations like Messaging Extraterrestrial Intelligence, METI, even advocate for proactive broadcasting, sending signals in hopes of contact. Yet caution remains. Stephen Hawking famously warned against active SETI, suggesting that advertising our existence to the cosmos might bring more danger than discovery. After all, we have no idea who might be listening. And still, the search continues. Why? Because SETI taps into something ancient and fundamental, the urge to connect, to know, to find out whether we are alone or among many. It's a scientific pursuit, yes, but also forces us to look up, to listen, and to contemplate our place in a galaxy that may be silent now, but is not necessarily empty. In every sweep of the sky, in every data set processed by cold algorithms and hopeful human eyes, lies the same question: is anyone out there? And if the answer is yes, how will we change? As our telescopes and spacecraft peer deeper into our own solar system, we find that the most promising places for life are not the planets themselves, but their moons, specifically, icy bodies hiding liquid oceans beneath their frozen shells. One of the most compelling of these worlds is Europa, a moon of Jupiter, whose quiet, pale surface hides a deep and mysterious ocean that may be one of the most habitable environments in the solar system. Europa is about the size of Earth's moon, yet it couldn't be more different. Its surface is a bright, gleaming layer of cracked and fractured ice, with almost no impact craters, suggesting that it's relatively young and actively reshaped. This icy shelf floats atop a vast, global subsurface ocean, perhaps 60 to 150 kilometers deep, making it more voluminous than all of Earth's oceans combined. And it's this hidden sea that has scientists captivated, because wherever we find liquid water on Earth, we tend to find life. The evidence for this internal ocean is substantial and multilayered. One of the first major clues came from the Galileo spacecraft, which orbited Jupiter in the late 1990s and early 2000s. As it passed Europa, it detected anomalies in the Moon's magnetic field, disturbances that suggested the presence of a conductive layer beneath the surface. The best explanation? A salty, liquid water ocean. Further supporting this idea are the surface features of Europa itself. Its icy crust is streaked with dark lines, fractures, ridges, and chaotic terrain, resembling ice flows on Earth's polar oceans. Some of these features appear to have broken apart and refrozen, hinting at a mobile layer beneath. This surface tectonics, rare for a moon, implies that internal heat is keeping water in a liquid state. But where does that heat come from? Unlike Earth, Europa doesn't have volcanic activity driven by a molten core. Instead, it experiences tidal flexing. As Europa orbits Jupiter, it's pulled and stretched by the planet's immense gravity, as well as by the gravitational tug of neighboring moons like Io and Ganymede. This constant tug-of-war creates internal friction, generating heat and preventing the ocean from freezing solid. Now consider this: a liquid water ocean, warmed by internal energy, in contact with a rocky seafloor. That combination is crucial. It raises the possibility of hydrothermal vents on the ocean floor, just like the ones on Earth's seabeds that teem with life. On our planet, Such vents support rich ecosystems powered not by sunlight, but by chemosynthesis, where bacteria use chemical reactions to produce energy. Entire food chains thrive there, utterly independent of the surface world. Europa's ocean may contain the same ingredients: heat, water, and minerals. And if it has hydrothermal activity, it could support microbial life, or even more complex organisms. The possibilities are extraordinary, not just for astrobiology, but for the philosophical implications. If life evolved twice in one solar system, it would imply that life is a universal phenomenon, likely to emerge wherever conditions allow. But is there direct evidence of life? Not yet. However, there have been some tantalizing hints. In 2012, the Hubble Space Telescope observed a plume of water vapor erupting from Europa's South Pole, shooting more than 160 kilometers into space. If these plumes are connected to the subsurface ocean, they offer a non-invasive way to sample it. No need to drill through the thick ice. These findings were later confirmed by further Hubble observations and reanalysis of Galileo data, which revealed the density drop and magnetic change as the spacecraft passed through one of these potential plumes. This discovery has electrified the scientific community. It means future missions could fly through Europa's plumes, collecting material from its hidden ocean without even landing. NASA has already designed such a mission, Europa Clipper, scheduled for launch in the late 2020s. This spacecraft will make dozens of close flybys of Europa, equipped with a suite of instruments to analyze its surface, measure magnetic fields, and most crucially, sample plume material if eruptions are active. It won't directly detect life, but it will search for biosignatures, organic molecules, chemical imbalances, or other markers that could suggest biological processes. In parallel, there are mission proposals for future landers and even ice-penetrating probes. These would be far more ambitious, requiring advanced technology to drill through kilometers of frozen crust. If successful, they could send submersible robots into the dark ocean beneath, exploring a world that has been sealed off for perhaps billions of years. And think of what that world might be like. A pitch-black ocean, warmed by internal heat, rich in salts and minerals. Perhaps it teems with alien microbes, clustering around vent fields. Perhaps, in the still waters of Europa's abyss, something stirs, something ancient, slow, and alive. It might not be intelligent. It might not be complex. But it would be life. Life not from Earth, not from our biosphere, but from an entirely separate origin. The discovery of even the simplest alien microbe on Europa would be a paradigm shift. It would tell us that life can emerge independently, that it is not a fluke or miracle, but a consequence of natural processes. And if it can happen here, then it can happen everywhere, on exoplanets, in distant star systems, on rogue worlds drifting through interstellar space. Europa, frozen and silent, may hold the answer to one of humanity's oldest questions: are we alone? And as our machines move closer, ready to drill, scan, and taste its ocean spray, we may be just years away from the moment that question is finally answered. While Europa has long fascinated scientists as a potential ocean world, another icy moon, orbiting farther out in the solar system, has quietly become one of the most promising places to search for alien life, and it's already ejecting its secrets into space. This is Enceladus, a small, frozen moon of Saturn, just 500 kilometers in diameter. Despite its modest size, Enceladus has drawn extraordinary attention because it is actively spraying material from its subsurface ocean into the vacuum of space. The discovery of this phenomenon was nothing short of revolutionary. In 2005, NASA's Cassini spacecraft flew by Enceladus and made a shocking observation: towering geysers of water vapor and ice crystals erupting from the moon's south pole. These plumes extend hundreds of kilometers into space and contain not just water, but salts, organic molecules, and even tiny silica grains. The source of these geysers? A global liquid water ocean beneath an icy shell, an ocean kept warm by tidal forces generated by Saturn's immense gravity. Here, for the first time in human history, we've found a world that is literally spitting its internal ocean into space, giving us the chance to sample an alien sea without landing, drilling, or even touching the surface. The fissures from which the geysers emerge are known as tiger stripes, long, dark fractures in the south polar ice, tens of kilometers long. Through these cracks, the subsurface water is vented outward in repeated bursts. Cassini flew through the plumes multiple times, using its instruments to taste the contents. What it found changed everything. The plumes weren't just water vapor. They contained salty water, molecular hydrogen, H2, methane, CH4, carbon dioxide, and a variety of complex organic compounds, including some with molecular masses over 200 atomic units. These findings suggest hydrothermal activity at the base of Enceladus's ocean, much like the deep sea vents on Earth that teem with life despite the absence of sunlight. And it's the presence of molecular hydrogen that's especially important. On Earth, hydrogen gas is a primary food source for certain microbial lifeforms, particularly those living in vent ecosystems. These microbes, called methanogens, combine hydrogen with carbon dioxide to produce methane and water. If similar conditions exist on Enceladus, the necessary ingredients for life, water, energy, and organic chemistry, are all in place. Furthermore, the composition of the ejected material indicates ongoing chemical reactions between the water and Enceladus's rocky core. These rock-water interactions not only produce hydrogen but also point to a seafloor environment potentially rich in nutrients. This is important because it implies that Enceladus isn't just a dead moon with a liquid layer. It might be chemically active, with all the right ingredients for habitability. Imagine a subsurface ocean, dark and pressurized, warmed by heat from tidal forces, laced with nutrients, and rich with organic molecules. If life were to exist anywhere beyond Earth, this is one of the best places to look. Cassini did everything it could during its 13-year mission in the Saturn system, but it wasn't designed to search for life directly. It had no microscopes, no sample return systems, and no ability to land. What it did provide, however, was a wealth of data that has transformed how scientists prioritize the search for life. As a result, planetary scientists and space agencies are now actively planning follow-up missions specifically designed to return to Enceladus and examine its geysers more closely. Concepts like Enceladus Orbolander, being studied by NASA, envision a spacecraft that could orbit Enceladus, fly repeatedly through the plumes, and eventually land to study the surface. The mission could carry instruments capable of detecting amino acids, lipids, microbial cells, or even DNA-like molecules, depending on how life, if it exists there, has evolved. And unlike Mars or Europa, where sampling often requires complex drills or rovers, Enceladus delivers samples to us. This means that a carefully timed flyby through its geysers could allow us to analyze material from the deep ocean without ever needing to penetrate the icy shell. This ease of access makes Enceladus one of the most cost-effective and high-reward targets in astrobiology. We can continue sampling the plumes, mapping their structure, measuring their composition across different time periods, and even searching for temporal changes, a sign that biological processes might be active. But there's a deeper, more profound angle to all this. If life is discovered on Enceladus, it would likely be independent of Earth, not transferred via meteors or panspermia, but a second genesis. It would represent a separate experiment by nature, a second example of life in the solar system. And two origins of life in one solar system would suggest that the universe is likely teeming with life. Even if the life found were microbial, it would answer one of humanity's most enduring questions: are we alone? And it would do so not through a mysterious signal from light years away, but from a tiny, icy moon orbiting a ringed gas giant in our own cosmic backyard. Enceladus reminds us that the universe hides its secrets in plain sight, in plumes, in fractures, in invisible oceans beneath frozen crusts. And thanks to missions like Cassini, and future explorers yet to come, we are finally learning how to listen. It's no longer just a hope or a guess. The signs are there, waiting in the mist that rises from Enceladus, whispering from the spray of a geyser a billion kilometers from home. While Europa and Enceladus beckon with the possibility of life as we know it, warm oceans, liquid water, and Earth-like conditions, there exists a world that offers a tantalizingly alien alternative. A place where lakes glisten in the golden twilight, rivers carve through valleys, and rain falls from hazy skies, not with water, but with liquid methane and ethane. This is Titan, Saturn's largest moon, and perhaps the most Earth-like world in the solar system, except it operates on an entirely different chemistry. Titan is a paradoxical place. It's both incredibly familiar and profoundly alien. Roughly 50% wider than Earth's moon and even larger than the planet Mercury, Titan has a thick, nitrogen-rich atmosphere, the only moon in the solar system to possess one. This atmosphere is denser than Earth's, veiling the surface in a constant orange haze due to complex hydrocarbon aerosols. Sunlight barely penetrates, and temperatures hover at a bone-chilling -179 degrees Celsius. And yet this freezing, shrouded world has weather, climate, and geological processes strikingly similar to our own. But instead of water, Titan's entire hydrological cycle is based on liquid methane and ethane. These hydrocarbons exist as liquids at Titan's surface temperature, forming rivers, lakes, seas, and even rain. In the polar regions, vast lakes and seas stretch for hundreds of kilometers. The largest of these, Kraken Mare, is bigger than Earth's Lake Superior. There are also signs of seasonal precipitation, cloud systems, and storms, suggesting that Titan's methane lakes may experience rainfall, evaporation, and possibly even methane snow. This alternate form of hydrology, so familiar yet so foreign, makes Titan an incredible laboratory for studying how life might evolve under different chemical conditions. On Earth, life depends on water as a solvent. It's where the chemistry of life happens. But scientists have long theorized that other solvents, like methane or ethane, could support life too, particularly if that life is based on a radically different biochemistry. This idea, once confined to science fiction, is now a serious field of research. Scientists at institutions like NASA's Astrobiology Institute and the SETI Institute are exploring how methanogenic life might function. Such life wouldn't use water at all. Instead, it might evolve cell membranes composed of acrylonitrile or other exotic compounds that remain stable in liquid methane. These cells wouldn't operate at warm temperatures, but would function in the extreme cold, with slow metabolisms and chemistry governed by the physics of cryogenic liquids. Titan may be the best real-world test case for these ideas. In fact, in 2015, scientists modeled a possible form of alien cell membrane they called an azotosome, composed of nitrogen, carbon, and hydrogen molecules, all of which are abundant in Titan's environment. Unlike Earth's phospholipid membranes, these hypothetical cells could be stable and flexible in liquid methane, offering a theoretical scaffold for methane-based life. But the intrigue doesn't stop at hypothetical life. Titan's chemistry is complex and prebiotic, meaning it may mirror the conditions that existed on early Earth before life began. The Moon's upper atmosphere is constantly bombarded by solar radiation and energetic particles from Saturn's magnetic field. These interactions drive a rich chemistry, forming tholin particles, complex organic molecules that fall like a light drizzle onto the surface. These tholins are believed to be precursors to the building blocks of life, such as amino acids and nucleotides. What's more, Titan may harbor a subsurface ocean of liquid water and ammonia beneath its crust. This ocean, warmer than the surface and protected from the cold, offers yet another potential habitat, one that could host water-based life, much like Europa or Enceladus. So Titan could conceivably support two types of biospheres, one exotic and methane-based near the surface, and another water-based deep below. The scientific community is so intrigued by Titan's potential that NASA has greenlit a revolutionary mission to explore it. The Dragonfly mission, set to launch in the 2030s, is not a rover, orbiter, or lander. It's a nuclear-powered rotorcraft, essentially a flying drone, designed to hop from site to site across Titan's surface. Dragonfly will study the chemistry of the atmosphere and surface, analyze organic compounds, and search for biosignatures. It will land near Titan's equator, in regions filled with dunes, icy rock, and tholin deposits. And over the course of its multi-year mission, it will move from one location to another, exploring riverbeds, ancient basins, and possibly even lake shores, gathering data that could tell us whether prebiotic chemistry, or something more, has taken root. The mission is expected to fundamentally alter our understanding of alien habitability. Because if Titan can host life with no dependence on water or sunlight, it would break open the definition of life itself. It would suggest that biology doesn't just follow one template, but adapts to whatever environment is available, finding a way in methane as it has in water. Titan also holds symbolic significance. It is a mirror of Earth, but eerily altered. It has mountains, dunes, clouds, rivers, and seas, but all forged in cold chemistry and alien physics. It reminds us that Earth is not the only place where nature carves landscapes, or where clouds roll across the sky. The mechanisms may differ, but the result is hauntingly familiar. And that familiarity is what grips our imagination. A moon, nearly 1 billion miles from the sun, encased in haze and cold, where rain falls on alien shores and rivers cut paths through icy terrain. A world that operates under a different set of rules but follows the same universal drive, to shape, to flow, to evolve. If life exists on Titan, it would be unlike anything we've ever encountered, not just extraterrestrial, but extra-chemical. It would prove that the universe doesn't merely repeat the blueprint of Earth but rewrites it in forms we've only begun to imagine. If life exists beyond Earth, whether in the oceans of Europa, the methane lakes of Titan, or even on distant exoplanets, it raises an equally profound question: where did it come from? Did life begin independently on each of these worlds, through separate chemical processes and unique origins? Or could life, once formed, travel through space, spreading from one world to another, seeding the cosmos with biology like pollen on the wind? This is the central idea of the panspermia theory, a concept that challenges our most deeply held assumptions about life's origins and possibilities. The word panspermia comes from the Greek pan meaning all, and sperma meaning seed. At its core, panspermia suggests that life, or at least its building blocks, can travel between planets, star systems, or even galaxies, carried by natural or artificial mechanisms. It doesn't try to explain how life began, but rather proposes that once life exists somewhere, it may not stay isolated. Instead, it could disperse, leapfrogging across cosmic distances and populating multiple worlds. There are several variations of the theory, ranging from natural and passive processes to active and deliberate distribution by intelligent beings. Let's begin with natural panspermia, the version most commonly explored in scientific literature. Imagine an asteroid impact on a life-bearing planet, say, Earth, billions of years ago. The impact is so powerful that it ejects chunks of rock into space, some of which escape the planet's gravity entirely. If those rocks contain microbial life, particularly hardy bacteria or spores, they may survive the ejection and the frigid, radiation-filled journey through interplanetary or even interstellar space. Eventually, some of these rocks could land on another planet, like Mars, Europa, or even a completely different solar system, where conditions might allow the microbes to awaken, replicate, and start life anew. This is not just idle speculation. We now know that rocks from Mars have landed on Earth, and vice versa. Over 250 Martian meteorites have been identified on our planet, with some showing signs of minimal heating, suggesting that if life had existed in them, it might have survived the journey. Microbial life on Earth is astonishingly resilient. Certain species of extremophiles, such as Deinococcus radiodurans, can survive high radiation doses, desiccation, and extreme temperatures. Tardigrades, microscopic animals, can survive in the vacuum of space, frozen or dehydrated, for years. Experiments conducted on the International Space Station have demonstrated that some microbial life can indeed survive exposure to outer space. Spores embedded in rock, protected from direct UV radiation, can remain viable for extended periods. This lends support to the idea that life could survive the journey inside the shielding of rock or ice. So, is it possible that life on Earth originated elsewhere? That we are the descendants of microbes that began on Mars, or even beyond? Some scientists, including Francis Crick, co-discoverer of DNA, entertained this notion. Crick even proposed a more radical form of panspermia, directed panspermia. Directed panspermia suggests that intelligent beings intentionally seeded life on other planets, either to preserve their species, spread biology, or conduct experiments. They might have sent spacecraft loaded with microbes, engineered to survive a landing on distant, potentially habitable worlds. This theory doesn't just ask how life traveled, it asks why. It frames life as a kind of cosmic mission, intentionally dispatched by entities we might never meet. Though speculative, directed panspermia raises important questions about our own behavior. As we prepare to send robotic probes to Mars, Europa, Enceladus, and Titan, planetary protection protocols are enforced to prevent forward contamination, accidentally seeding these worlds with terrestrial microbes. If we are so cautious about contaminating other planets today, what if another civilization, long ago, was not? Moreover, even accidental panspermia may already be underway. Mars rovers, despite rigorous sterilization, might still carry bacterial remnants. Our spacecraft, orbiters, and landers might already be introducing microbes into the solar system, where they could one day thrive if conditions allow. This flips the panspermia model around. We may be the seeds. Then there's interstellar panspermia, the idea that life could leap from one star system to another. The distances involved are enormous, and the time spans mind-bending, millions of years to travel even a few light years. But some models suggest that stellar drift, over billions of years, could allow debris from one system to enter another. Comets, with their icy exteriors and protective cores, could serve as ideal life capsules. The detection of interstellar objects like Oumuamua and Borisov shows us that material does cross between systems. What if, instead of rocks, they carried life? Supporting this idea is the observation that many amino acids and organic molecules have been found in meteorites and comets. These include glycine, a simple amino acid, and complex hydrocarbons. Some molecules critical for life may form in deep space, even in cold interstellar clouds, and then be delivered to young planets during their formation. Thus, the seeds of life may not just be drifting from planet to planet, but may be embedded into the very dust from which solar systems form. If this is true, then life is not an earthly anomaly, but a cosmic pattern built into the universe's very fabric. But panspermia is more than a theory, it's a philosophical earthquake. It shifts the origin of life from a specific place to a continuum of cosmic events, and it reframes life not as a local accident, but as a migratory force, moving, surviving, adapting across the stars. If life can spread across planets, then the universe is not silent and empty. It is fertile. It is connected. And every living cell, on Earth or beyond, might be part of a vast, ancient lineage stretching backward across galaxies and forward into possibility. Panspermia doesn't eliminate the mystery of life. It expands it. It replaces one origin with 1,000 routes, and in doing so, it may explain why the universe feels so ready to receive life, because it's already been seeded. When we think about the search for life, our focus often zooms in on planets, those rocky worlds circling stars within that delicate range known as the habitable zone. But as we begin to ask deeper questions about where life might flourish, it becomes clear that the planetary scale isn't enough. To truly understand life's potential, we have to look at the galaxy itself as a complex ecosystem. Just as planets have regions better suited for biology, entire parts of a galaxy may be more or less conducive to life. This brings us to one of the most intriguing concepts in astrobiology: galactic habitability zones. This idea takes the same logic we apply to habitable planets and expands it across the vast architecture of a galaxy. It's based on a simple but profound premise: not all regions of a galaxy are equally safe or fertile for life to emerge and evolve. Some areas are bathed in high-energy radiation, others lack the heavy elements necessary for forming rocky planets, while a few zones may strike a perfect balance, not too dangerous, not too barren. Let's take our own Milky Way as an example. It's a sprawling spiral galaxy over 100,000 light-years across, with hundreds of billions of stars arranged in spiral arms, a central bulge, and a diffuse halo. Somewhere in one of those arms, about 27,000 light-years from the galactic center, lies our Sun, a fairly average star in a relatively quiet neighborhood. And that placement might not be coincidental. According to the theory of galactic habitability, the galactic habitable zone, GHZ, is a ring-shaped region within a galaxy where conditions are optimal for life to arise and persist. It's not a sharply defined area, but more like a probabilistic belt where the likelihood of stable, life-supporting planets is higher. In the Milky Way, this zone is thought to extend from roughly 7 to 10 kiloparsecs, about 22,000 to 32,000 light-years, from the center, and Earth lies right in it. But what defines this sweet spot? Several factors come into play. The first is metallicity, which, in astronomy, refers to the abundance of elements heavier than hydrogen and helium. These metals are essential for building rocky planets, moons, and even organic molecules. In the inner parts of the galaxy, near the bulge, metallicity is generally high, but so is stellar density and radiation. There, stars are packed closely together, and supernovae are far more frequent. These violent explosions can sterilize nearby planets, erasing any potential biospheres in an instant. Move too far out toward the galactic halo, and the opposite problem arises. While the space between stars is vast and relatively safe from radiation, metallicity drops off significantly. With fewer heavy elements, the chances of forming rocky, Earth-like planets diminish. You might get gas giants or barren worlds, but not the kind of complex chemistry that fosters life. The galactic habitable zone is that middle ground, rich enough in metals to form terrestrial planets, but far enough from the chaos of the core to avoid being bathed in deadly radiation. It's a region of chemical fertility and relative stability, where solar systems like ours can survive long enough for life to evolve. And this matters enormously when we think about how rare or common intelligent life might be. If intelligent civilizations need billions of years to evolve, they require stable stellar environments, places where they won't be wiped out by nearby supernovae or gamma-ray bursts. That rules out vast swaths of the galaxy where stars burn fast, die young, or explode violently. Studies also suggest that galactic dynamics play a role. As stars orbit the center of the galaxy, they migrate over time. Some systems may begin in hazardous zones and drift into more habitable ones, or vice versa. Our own solar system may have wandered through various regions over the last 4.5 billion years. These galactic journeys affect the amount of radiation a system receives, the stability of planetary orbits, and the influx of comets and asteroids. Another critical factor is the frequency of catastrophic events. Certain regions, particularly near dense star clusters, are more likely to experience nearby supernovae or encounter rogue stars. A close pass by another star could gravitationally disrupt a planetary system, flinging planets into space or destabilizing orbits. In the relative quiet of our galactic suburb, such events are less likely. But even beyond physical safety and chemical composition, there's the question of time. The GHZ isn't just a spatial concept, it's also temporal. Some regions of the galaxy became habitable earlier than others. For example, planets near the galactic core formed first, due to the higher star formation rate and abundance of heavy elements. If life managed to evolve in those areas before supernovae became too frequent, it could be billions of years older than life on Earth. Alternatively, outer regions may just now be reaching sufficient metallicity to support Earth-like planets, meaning life there could be just beginning. This gives rise to an intriguing speculation. What if life emerged multiple times throughout the galaxy, but was extinguished repeatedly due to environmental instability? Only those civilizations lucky enough to reside in the GHZ, and stable enough to survive long-term, would make it to the point of advanced intelligence. Perhaps we're not alone, but we are among the few survivors. This framework also allows for evaluating other galaxies. In larger, more metal-rich galaxies, GHZs may be wider or more complex. In dwarf galaxies or irregular ones, habitability might be far more constrained. Some researchers have even proposed that elliptical galaxies with high metallicity and low star formation rates could harbor more stable GHZs than our Milky Way. It's worth noting that the GHZ model is still evolving. Some scientists argue that life may be more adaptable than we think, that even in regions of high radiation, life might evolve radiation resistance, or retreat underground or underwater. Others point out that our definition of metallicity may change if we discover forms of life that don't rely on the same chemistry as us. But what the galactic habitability model does, unquestionably, is reframe our search for life. It tells us that we shouldn't just look for the right planets, or the right stars, but for the right neighborhoods in the galaxy. That where you live in the Milky Way may matter as much as what kind of world you live on. In this way, the universe becomes a grand tapestry of potential, a multidimensional map not just of stars and matter, but of life's likelihood, woven into the geometry of galaxies themselves. And here we are, floating in the quiet arms of a spiral galaxy, in a habitable system, on a habitable planet, in a habitable time, perhaps not by chance, but by cosmic design. When considering the vastness of the universe and the potential existence of alien civilizations, we often imagine what they might look like, how they might communicate, or even where they might live. But there's another dimension, perhaps even more telling, that can be used to classify intelligent life: how much energy a civilization is capable of harnessing and utilizing. This concept was formalized in one of the most influential frameworks in the search for extraterrestrial intelligence, the Kardashev scale. Proposed in 1964 by Russian astrophysicist Nikolai Kardashev, the scale isn't based on biological traits, technology level, or philosophical complexity. It is purely based on energy consumption, a metric that transcends biology and culture. Kardashev proposed that the more advanced a civilization is, the more energy it needs, and thus, the more energy it learns to control, harvest, and direct. The original Kardashev scale included 3 types of civilizations. Type 1, a civilization that can use and store all of the energy available on its home planet. This includes everything from solar energy falling on the surface to geothermal heat, oceanic energy, and even the full power of its atmosphere and tectonics. Earth is not yet a Type 1 civilization. We're close, perhaps around Type 0.73, but we still rely heavily on fossil fuels and haven't yet optimized global-scale energy use. To reach Type 1, humanity would need to sustainably capture and manage roughly 10^1 watts of power. Type 2, a civilization that can harness the total energy output of its home star. This is where things begin to sound truly alien. A Type 2 civilization might build megastructures, such as a Dyson sphere or Dyson swarm, to envelop its star and collect its energy output directly. The energy of a single star, on the order of 10^2 watts, would be used to power unimaginable projects, interplanetary terraforming, stellar-scale computing, or deep space colonization. If such civilizations exist, they would likely be detectable through their waste heat emissions, which would show up as infrared radiation around the star. Type 3, a civilization that can command the energy output of an entire galaxy, a staggering 10^3 watts or more. These would be very powerful beings compared to us, potentially capable of re-engineering stars, moving planets, or manipulating black holes. A Type 3 civilization might control the trajectories of entire star systems, or create networks of artificial intelligence that span galactic arms. If we ever observed stars dimming en masse, or unexplained galactic-scale structures, it could suggest the presence of such a civilization. They would be virtually impossible to ignore, unless they deliberately conceal themselves. But the Kardashev scale is more than just a theoretical curiosity. It provides a structured way to think about progress, technological growth, and the future of life. It shows that if intelligence survives long enough, it doesn't just grow, it expands its reach over nature, from planets to stars to galaxies. And it gives us a roadmap for what we might expect to find, or become. One of the most interesting uses of the scale has come from thinkers like Carl Sagan, who proposed refining it into a continuous scale. Instead of discrete types, he used a logarithmic formula to calculate a civilization's level based on its actual energy consumption. By this measure, humanity, as of now, is Type 0.72 to 0.73. This helps us ask the question, how far do we have to go, and how fast can we get there? If we continue advancing in energy use and technology without self-destructing, we could reach Type 1 status within a few centuries. But it's not just about generating more energy, it's about doing so sustainably, without destroying our environment. After all, if a civilization burns through its biosphere in pursuit of power, it will never reach the next stage. For Type 2 and 3 civilizations, the challenges become cosmic. To build a Dyson sphere, one would need to disassemble planets for raw materials, coordinate megastructures over astronomical distances, and maintain them for millions of years. And to control a galaxy's energy would require near-omniscient technology, possibly involving artificial general intelligence, self-replicating machines, or even biology-enhancing integration with quantum computing. These civilizations would likely have overcome war, scarcity, disease, and even death, operating on timelines and moral frameworks incomprehensible to us. So, where are they? That's where the Kardashev scale intertwines with the Fermi Paradox. If the galaxy is old enough, and advanced civilizations become Type 3 within millions of years, why don't we see any evidence? Why haven't we detected the infrared waste heat from Dyson structures, or spotted large-scale engineering projects across the stars? Several possibilities emerge. Perhaps Type 3 civilizations are rare because intelligence usually destroys itself before reaching that point. This would align with the Great Filter hypothesis. Or maybe advanced civilizations transcend physical energy use, becoming digital, quantum, or existing in simulated realities with minimal detectable output. Or perhaps they're deliberately hiding, following a galactic non-interference directive, ensuring that emerging civilizations, like ours, aren't influenced or destroyed. There's also the sobering thought that some civilizations might not pursue energy growth. Maybe they reach a stable, sustainable equilibrium at Type 1 or 2 and decide not to expand further. The Kardashev scale, after all, is based on the assumption that intelligence seeks more power. But what if intelligence evolves to seek balance instead of domination? Despite the uncertainties, the scale remains a powerful tool for SETI, search for extraterrestrial intelligence. Researchers have scanned galaxies in infrared for signs of Type 3 civilizations. To date, none have been definitively found, but the absence of evidence is not evidence of absence. It might simply be that we've just begun to look, or that we lack the sensitivity to detect them yet. In another light, the Kardashev scale is a mirror, reflecting not only what we might find out there, but what we could become. It offers a vision of a civilization mature enough to manage an entire planet, wise enough to harvest a star, and bold enough to reach across galaxies. In an age of climate crisis and energy challenges, the first step, becoming a Type 1 civilization, feels both urgent and uncertain. But if we succeed, we would not only secure our place in the cosmos, we'd also join a path that might one day lead to the stars themselves. In the grand quest to discover intelligent life beyond Earth, perhaps no concept has captivated both scientists and science fiction dreamers alike as much as the Dyson sphere, a hypothetical megastructure so vast, so awe-inspiring, that its very existence would serve as irrefutable proof of an advanced alien civilization. First proposed in 1960 by physicist and mathematician Freeman Dyson, the Dyson sphere wasn't envisioned as a solid, sci-fi shell encasing a star, as often portrayed in films and books, but as a conceptual solution to a very real problem: the escalating energy needs of a growing technological species. The basic idea is as elegant as it is radical. As a civilization becomes more advanced, it will inevitably consume more energy. Eventually, it may reach a point where the energy available on its home planet becomes insufficient for its needs. The next logical step would be to harness the full energy output of its parent star. After all, our Sun emits over 10^2 watts of power every second, billions of times more than all of humanity's current consumption combined. Most of that energy is lost into space. A sufficiently advanced civilization, therefore, might construct a vast array of satellites, mirrors, or energy-collecting structures that orbit the star in a formation, absorbing or capturing the stellar output. This structure, known as a Dyson swarm or Dyson shell, wouldn't be a single rigid sphere but rather a distributed cloud of solar collectors, each independently orbiting the star. These could beam energy back to their home world, or store it for deep space projects, computation, terraforming, or any number of activities beyond our imagination. Dyson's original suggestion was purely scientific. If such a structure existed, it would likely re-radiate the star's energy in the infrared. So, he proposed, why not look for such infrared anomalies? That idea still powers much of modern SETI, search for extraterrestrial intelligence, thinking. In fact, Dyson spheres have become one of the most plausible and testable technosignatures, observable evidence of large-scale engineering by intelligent beings. If we can't find alien signals, perhaps we can detect their technology, especially when it manipulates something as massive as a star. And we've started looking. Astronomers have used infrared space telescopes like IRAS, Infrared Astronomical Satellite, and WISE, Wide Field Infrared Survey Explorer, to scan the skies for stars that appear dim in visible light but unusually bright in infrared, a possible sign that some of their visible light is being blocked and re-emitted as waste heat by artificial structures. While no confirmed Dyson spheres have been found, these surveys have yielded hundreds of infrared excess candidates, stellar systems that warrant further investigation. Perhaps the most famous case is KIC 846-2852, also known as Tabby's star. In 2015, astronomers observed that the star was undergoing strange, irregular dimming events, dips in brightness up to 22%, far more than a planet or comet could account for. This immediately led to speculation. Could it be a partial Dyson swarm in progress? Though natural explanations have since taken precedence, such as clouds of dust or fragmented comets, the case reignited interest in Dyson spheres and raised public awareness about how they might be detected. The beauty of the Dyson sphere idea is that it provides a scalable, testable signature of advanced life. A Type II civilization on the Kardashev scale, one that harnesses the energy of its star, might not build a complete sphere, but even a partial Dyson swarm would produce observable changes in a star's spectrum. It might emit more in the mid-infrared range, show signs of missing visible light energy, or even exhibit strange light curves as collectors orbit and block some of the starlight. Some futurists have proposed variations, like a Dyson ring, which would be a band of satellites orbiting along a single plane, or Dyson bubbles, in which solar sails counteract the star's gravity to hold stationary collectors in place. In all of these designs, the idea remains consistent: capture as much stellar energy as possible and redirect it for use. Now, think for a moment about the engineering required. To build even a modest Dyson swarm would involve disassembling entire planets, possibly converting the mass of a Mercury-sized world into trillions of solar collectors. It would require precise orbital mechanics, stable construction in vacuum, and robust materials that can withstand solar radiation and micrometeorite impacts for thousands or millions of years. It's a project not for a single species, but possibly for a civilization spanning centuries or millennia, coordinating the efforts of AI systems, robotic constructors, and space-based infrastructure. And yet, to an advanced species, this might be a logical, even essential step. Imagine needing energy for galaxy-wide communications, megascale computation, such as running simulations or artificial realities, or propelling worldships across light years. A star, once seen as a distant source of heat and light, becomes an engine, a battery, a generator powering the next phase of existence. The implications for us are equally profound. The Dyson sphere concept teaches us that if intelligent life persists long enough, it must grow in its energy mastery. And if such civilizations are common, we should expect the galaxy to contain visible signs of astroengineering. The fact that we haven't found any yet ties into the Fermi Paradox. Either they don't exist, or they do and they're hiding, or perhaps we're still too early in the search to know what to look for. Some thinkers have even suggested that advanced civilizations might cloak their energy use, or emit it in non-electromagnetic ways to remain undetectable. Others propose that they might abandon physical stars altogether, moving to digital or quantum realms where energy requirements are lower and no megastructures are necessary. But until we have more data, Dyson spheres remain one of the most logical and testable predictions of advanced extraterrestrial engineering. They also ignite the imagination. As humanity looks to the stars, we too must grapple with our future energy needs. Some scientists envision solar collectors in Earth orbit, space-based power stations, and eventually interplanetary energy networks. These could be our first baby steps toward building our own Dyson swarm, centuries or millennia from now. And if we ever detect one, an actual Dyson sphere humming around a distant star, it would mean we're not alone, that others have not only survived the perils of their adolescence as a civilization, but have transcended their planetary limits and become masters of their stars. In the end, the search for Dyson spheres is more than just a hunt for aliens. It's a search for what's possible, a reflection of what we might one day become. It asks us to look at the sun not just as a light in the sky, but as a future power source, and to imagine the incredible things that life, wherever it may arise, might build in its pursuit of knowledge, survival, and creation. If life is statistically likely to emerge throughout the universe, if microbial organisms can form in warm oceans beneath icy moons, or if planets orbiting distant stars show signs of atmospheric biosignatures, then we should expect the cosmos to be brimming with life, some of it advanced. And yet, when we listen, we hear silence. When we look, we see emptiness. No galactic empires. No artificial megastructures. No signals crossing the void. This eerie contradiction is what the Fermi Paradox highlights. But the most sobering attempt to answer that paradox comes in the form of a theory that is as unsettling as it is plausible: the Great Filter Hypothesis. At its core, the Great Filter proposes that some catastrophic barrier, some process or series of challenges, is so difficult to overcome that almost no civilizations make it past a certain point. It's not just that life is rare. It's that something stops it from progressing to the point of interstellar communication, travel, or visibility. This filter could lie in our past, or it could be ahead of us. And depending on where it is, the implications for humanity are either hopeful or deeply ominous. To understand the Great Filter, consider the vast chain of events that must happen for a civilization like ours to arise and thrive. It begins with the formation of the right kind of star, one that is stable and long-lived. Then you need a rocky planet, in the habitable zone, with water, organic chemistry, and a stable climate. Even with those conditions, life must emerge, a transition from non-living molecules to self-replicating entities. That's step one. From there, it must evolve, survive, and become increasingly complex. But even multicellular life isn't the end goal. You need tool-using intelligence, civilization, language, agriculture, technology. Then, even further down the line, you need spaceflight, the mastery of energy, long-term survival and complex systems. At any point along this path, things could go wrong, and perhaps they usually do. So, the Great Filter asks, which of these steps is nearly impossible? Which hurdle is so astronomically unlikely or dangerous that almost no life forms make it through? If the Great Filter lies behind us, then the emergence of intelligent, space-faring life on Earth is an astonishing anomaly, a once-in-a-galaxy event. That would mean we're extremely lucky. Maybe abiogenesis, the origin of life from non-life, is nearly impossible. Maybe complex life rarely evolves from microbes. Or maybe intelligent life almost always destroys itself before it can achieve anything lasting. In this version, we are the exception, a rare spark that managed to pass through a narrow gate. And if that's true, it means the galaxy may be quiet not because others are hiding, but because they never made it. In that case, our future may be relatively bright. But what if the Great Filter lies ahead of us? What if life is common, intelligent life is common, but some catastrophe consistently wipes it out before it can expand beyond its solar system? This is the darker possibility. Maybe all civilizations eventually succumb to technological self-destruction, nuclear war, ecological collapse, artificial intelligence run amok. Maybe once a species gains a lot of powers, it inevitably destroys itself before reaching the stars. In this view, the silence of the cosmos is a warning, a graveyard of civilizations that came close, but failed. There are other possibilities. Perhaps the universe is filled with intelligent life, but the Great Filter is not about survival, but about detectability. Civilizations may evolve beyond the need for physical expansion or electromagnetic communication. They might upload their consciousness into quantum substrates, retreat into simulated realities, or choose to remain silent to avoid predation. Or maybe the great filter is imposed externally, a dark forest scenario in which civilizations remain quiet out of fear of being discovered and destroyed by others. Another possibility is that interstellar travel and colonization are simply far more difficult than we imagine. Perhaps faster than light travel is impossible, and even slower than light journeys are economically or biologically unfeasible. The filter could then be a practical limitation, not a deadly one. Life exists, but it's trapped in isolated pockets of the galaxy, unable to connect. This idea forces us to ask hard questions about our own path forward. If we are approaching the great filter, what form might it take? Could it be climate change, eroding the habitability of our own world before we can establish off-world colonies? Could it be resource exhaustion, or ecological overshoot? Could our technological development outpace our wisdom, leading us to create tools we cannot control? And if we are beyond the filter, if we are, indeed, rare survivors, what responsibility does that place upon us? Should we be racing to become a multiplanetary species, to protect the spark of consciousness that has emerged on this pale blue dot? If intelligent life is rare, then our existence is not just a local miracle, it's a cosmic responsibility. One of the most chilling interpretations of the great filter is that we may never know where it is. We might not recognize it until it's too late. It could come in the form of an innovation that seems innocuous at first, an AI breakthrough, a biological experiment, a self-replicating machine, and only in hindsight would we understand that it was the precipice. Or perhaps we are already past it, and we don't realize how exceptionally rare our path has been. For researchers in astrobiology, the implications of this theory shape how we interpret data. For example, if we find primitive life on Mars, or microbial fossils on Europa, or even biosignatures on exoplanets, it would suggest that the early steps in life's development are easy. That would make it more likely that the filter lies ahead, and the harder transitions from life to intelligence, and from intelligence to sustainability. On the other hand, if we scour the universe and find no signs of life anywhere else, it could suggest that the filter is behind us, perhaps even at the very first step, the origin of life itself. In that case, we may be alone, but also safe from the worst possibilities. In either case, the great filter brings an extraordinary urgency to our scientific exploration and our collective choices. It reframes the silence of the stars not as indifference, but as a mystery filled with existential meaning. It challenges us to look inward as we look outward, to recognize that our greatest threat may not come from the cosmos, but from ourselves. And so, the great filter may not only be a cosmic barrier. It may be a test of maturity, a threshold every intelligent species must face. To pass through it is to transcend self-destruction, to build a future worthy of the stars. Whether we succeed, or become just another whisper in the silence, remains to be seen. In the vastness of the cosmos, with its hundreds of billions of galaxies, each containing billions of stars and potentially trillions of planets, the idea that Earth might be the only world with intelligent life seems almost absurd. And yet, that's exactly what the rare Earth hypothesis dares to suggest. Not that life is impossible elsewhere, but that complex, intelligent life is so exceedingly rare that it may exist only on a handful of planets, or just one. While the Great Filter hypothesis asks where civilizations go wrong, the rare Earth hypothesis poses a different, though equally profound question. What if everything had to go exactly right, for billions of years, for a planet like Earth to produce intelligent beings? What if the emergence of life, especially complex multicellular life, requires such a finely tuned combination of environmental, astronomical, geological, chemical, and biological factors that it's not just rare, it's exceptionally improbable? Formulated most famously by paleontologist Peter Ward and astronomer Donald Brownlee in their 2000 book Rare Earth, Why Complex Life is Uncommon in the Universe, the theory doesn't argue against the possibility of simple microbial life elsewhere. On the contrary, it accepts that bacteria or single-celled organisms may be abundant. But when it comes to intelligent, conscious beings, the kind that build telescopes and ponder their place in the universe, the hypothesis is grimly skeptical. Let's break down the factors it considers. First is the presence of a galactic habitable zone, a safe region in a galaxy like the Milky Way where radiation levels are low and the chemical elements needed for planets and life are sufficiently abundant. Earth's location, far from the dangerous center, but not too far into the chemically poor outskirts, may be just right. Too much radiation, or too few heavy elements, and the chances of life fall dramatically. Then comes planetary habitability. Earth isn't just in the Goldilocks zone, around the Sun, it also has a stable orbit, a relatively circular path that prevents extreme climate fluctuations. It orbits a G-type star, stable and long-lived, not prone to the violent flares and bursts that plague red dwarfs. Our Sun is not so massive that it burns out quickly, nor so small that it lacks the necessary warmth. That balance alone filters out millions of other planetary systems. Next is the presence of a large moon. Earth's moon is abnormally large compared to the planet it orbits. It helps stabilize Earth's axial tilt, which keeps the seasons from becoming too extreme. Without it, Earth's axis might wobble wildly, creating chaotic climate shifts that could prevent the development of stable ecosystems. That moon was likely formed by an incredibly rare, precisely angled giant impact event, the kind that might happen only once in hundreds of millions of planetary collisions. We must also consider plate tectonics, a feature not observed on any other known planet in the solar system. Tectonic activity plays a critical role in Earth's long-term carbon cycle, regulating atmospheric CO2 and preventing runaway climate states like Venus's hellish greenhouse effect or Mars's total atmospheric collapse. It also recycles nutrients and reshapes continents, fostering evolutionary diversity. Without plate tectonics, Earth's climate might have collapsed eons ago. Another rare Earth feature is the presence of liquid water on the surface for billions of years. While water may be common in the universe, maintaining stable oceans over vast timescales requires the right atmospheric pressure, temperature, and solar output, conditions that can be easily disrupted. We must also not forget Earth's magnetic field, a result of its molten iron core. This invisible shield protects the surface from solar and cosmic radiation, preserving the atmosphere and shielding DNA from mutations that could devastate emerging life. And then there's Jupiter, the silent guardian of the inner solar system. As a massive gas giant with immense gravity, Jupiter acts like a cosmic vacuum cleaner, deflecting or absorbing comets and asteroids that might otherwise slam into Earth. Without it, our planet would have faced more frequent mass extinctions, potentially resetting evolution each time life began to gain complexity. The rare Earth hypothesis weaves all of these factors together into a tapestry of staggering improbability. It argues that while microbial life may emerge relatively easily in the right conditions, complex life depends on a chain of coincidences, each one filtering out billions of other worlds. Even if just one of these factors were absent, a moon, a magnetic field, plate tectonics, or a shielding gas giant, Earth might still be a lifeless rock. And yet, even with all of these ingredients, intelligent life took 4 billion years to evolve on Earth. For the vast majority of that time, life remained microbial. Multicellular organisms only appeared in the last 600 million years. Homo sapiens have existed for just 300,000 years, a blink in geological time. That alone suggests that intelligence is not an evolutionary inevitability. It's not the end goal of life, it's an outlier. If the rare Earth hypothesis is correct, then the reason we haven't heard from alien civilizations isn't because they're hiding, or because they died out, but because they never existed. We may be in a galaxy teeming with bacteria, but devoid of engineers, poets, or philosophers. This has staggering implications. On one hand, it paints a lonely picture of the universe, one in which we are not just rare, but unique in our consciousness. On the other hand, it underscores the preciousness of our existence. If complex life is rare, then Earth is not just another planet, it is a miracle of cosmic odds, a cradle of thought floating in a sea of silence. And yet, it's worth remembering that the rare Earth hypothesis is still a hypothesis. Our sample size is 1 Earth. We have no definitive evidence of even microbial life elsewhere, much less intelligent life. Every new exoplanet discovered, every signal analyzed, every sample returned from Mars or Europa, serves as a data point in a cosmic puzzle that is far from complete. Some critics argue that the hypothesis may be too pessimistic, that it underestimates the adaptability of life, or overstates the improbability of certain conditions. After all, life on Earth has survived 5 mass extinctions, adapted to deep-sea vents, nuclear reactors, and the driest deserts. It's proven to be more robust and more versatile than we ever imagined. Even so, the rare Earth hypothesis remains one of the most sobering responses to the Fermi Paradox. It doesn't assume catastrophe or malevolence. It simply says, you're here because you beat the odds, and the odds are not in anyone's favor. If that's true, then our responsibility becomes even greater. We are not just curious wanderers in a galaxy of thinkers. We may be the only ones capable of looking back at the stars and asking why they're silent. We may be the cosmos becoming aware of itself, and it may be our task not only to survive, but to preserve and spread consciousness to ensure that the miracle of thinking life doesn't end here. When we ponder the origins of life, it's easy to think only in terms of oceans and microbes, of warm little ponds or hydrothermal vents. But the truth is that life's story stretches far beyond Earth, beyond our solar system, and even beyond our galaxy. It is a tale written in the stars, literally. For the raw materials that make life possible were not born here, but were forged in the hearts of ancient stars, scattered across the universe in cosmic explosions, and later gathered into planets like ours. This is the grand narrative of the cosmic evolution of life, where biology is inextricably tied to astrophysics, and the emergence of organisms is just one chapter in a much larger cosmic epic. It all begins with the Big Bang, roughly 13.8 billion years ago. In those first moments, the universe was unimaginably hot and dense, and only the lightest elements existed, primarily hydrogen and helium, with trace amounts of lithium. These elements are too simple to form complex molecules, let alone life. There were no planets, no oxygen, no carbon, just a sea of gas drifting in expanding space. The universe was, for a time, lifeless and dark. Then came the first stars. Through gravitational collapse, massive clouds of hydrogen and helium began to coalesce, igniting nuclear fusion in their cores. These stars were titans, larger and shorter-lived than our Sun. And in their hot, dense interiors, they began to forge the elements of life: carbon, nitrogen, oxygen, sulfur, phosphorus, iron, the building blocks of DNA, proteins, and cell membranes. When these stars reached the end of their lives, they didn't go quietly. They exploded as supernovae, sending their enriched guts flying across the cosmos. These cosmic detonations seeded the interstellar medium with heavier elements, forming the raw material for the next generation of stars and planets. It was in these enriched clouds that our own solar system eventually formed, billions of years later, out of second or third generation stardust. You, reading this right now, are made of atoms that were forged in those ancient stars. As the famous astronomer Carl Sagan put it, "We are made of star stuff." That isn't poetry. It's a literal truth. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, it all came from stellar alchemy. This idea, that life's chemical ingredients are not unique to Earth but universal, transforms the way we think about biology. Carbon, for instance, is an extraordinarily versatile atom. It can form long chains, rings, and complex molecules, making it the foundation of organic chemistry. And we find carbon everywhere in the universe, in interstellar gas clouds, on comets, in meteorites, and on distant exoplanets. The same goes for water. The Hubble and James Webb Space Telescopes have detected water vapor in the atmospheres of exoplanets and moons. Comets, those icy visitors from the outer reaches of our solar system, are loaded with water, carbon compounds, and amino acids. Some scientists even believe that Earth's water and organic molecules may have arrived via comet or asteroid impacts in its early history, linking planetary evolution directly to the chemistry of space. Then there's amino acids, the building blocks of proteins. These too have been found on meteorites that crash-landed on Earth, unchanged for billions of years. Even more astonishingly, some amino acids recovered from space rocks are not the same chirality as those found on Earth, suggesting an extraterrestrial origin that predates our planet's biosphere. This cosmic delivery system points to a chemical continuity throughout the universe, blurring the line between organic and inorganic, between life and the stars that birth it. So, what does this mean for the search for alien life? It means that wherever the conditions are right, liquid water, stable temperatures, energy sources, and these fundamental elements, life might emerge. Because the materials that created life on Earth are not unique to Earth. They are the common language of the cosmos, available to any world fortunate enough to host the right chemistry over long enough timescales. Astrobiologists refer to this as universal biochemistry. The hypothesis is that while alien life might differ in form, tentacled, crystalline, or microbial, the chemistry that underpins it would probably resemble our own. Because the periodic table is the same across the universe. Because physics works the same in every corner of spacetime. The electrons orbit atoms the same way on Kepler 186f as they do on Earth. This is where cosmic evolution becomes more than a poetic phrase. It is a scientific reality. From the fusion in stars to the formation of planets, from the emergence of complex molecules to the evolution of consciousness, life is a natural consequence of cosmic processes. Not guaranteed, not inevitable, but permitted, and perhaps encouraged, by the very physics that governs galaxies. And we see hints of this in the diversity of life on Earth. The fact that extremophiles, organisms that thrive in conditions previously thought uninhabitable, can live in boiling acid pools, under kilometers of ice, or around hydrothermal vents, shows that life is not fragile and rare, but tenacious and adaptable. It can emerge and persist even in extreme environments that resemble alien worlds. This has led many scientists to propose that the universe may be pregnant with life, waiting for the right spark. Every rocky planet, every subsurface ocean, every atmospheric cloud layer could be a laboratory of biology in progress. Whether it's Europa, Enceladus, Titan, or a rocky exoplanet in the habitable zone of a red dwarf star, the universe has had billions of years to roll the evolutionary dice. And perhaps life is not limited to one genesis per planet. If life's ingredients are everywhere, and its conditions are varied, then perhaps life arises repeatedly, independently, and frequently. Maybe Earth had multiple genesis events. Maybe other worlds did too. The cosmic evolution of life also opens up the possibility of life that is not carbon-based, though carbon remains the most likely candidate due to its flexibility. Some scientists have speculated about silicon-based life, ammonia solvents, or even plasma-based consciousness in the atmospheres of gas giants. These remain theoretical, but they remind us that life, as we know it, is just one chapter in a story that could take on countless forms. Ultimately, when we trace the origins of life back through the eons, we find ourselves staring not into a petri dish, but into the heart of stars. We are not separate from the cosmos, we are the cosmos made alive. We are the byproduct of ancient processes, nuclear fusion, stellar death, gravitational collapse, that happened on a scale we can scarcely imagine. And if those processes played out here, they surely played out elsewhere. So, we look to the skies not just for aliens, but for ourselves. For our own beginnings. For our cosmic cousins born from the same hydrogen clouds and stitched together by the same star-forged atoms. The universe has the ingredients. The question is whether it has used them again. In an era where our reach into the cosmos has never been greater, where telescopes pierce deeper into the galactic night and radio arrays sweep the heavens for whispers of intelligence, a monumental effort has emerged, one that embodies the very heart of humanity's desire to not just explore the stars, but to find out if someone, somewhere, might be listening back. This is the Breakthrough Listen Project, a $100 million initiative launched with the singular mission of answering one of the oldest and most profound questions in science and philosophy. Are we alone in the universe? Announced in July 2015 by physicist Stephen Hawking, tech investor Yuri Milner, and a consortium of leading astronomers, the Breakthrough Listen Project was founded on an ambitious premise: to conduct the most comprehensive, rigorous, and wide-ranging search for extraterrestrial intelligence, SETI, in history. And it doesn't just stop with funding a few radio dishes, It represents a turning point in how seriously mainstream science now approaches the search for intelligent life. Historically, SETI has always walked a delicate line. Underfunded, often dismissed as fringe, and reliant on borrowed telescope time, the early decades of SETI research were defined by passionate perseverance rather than institutional support. But the Breakthrough Listen project changed that by infusing the field with unprecedented resources, not just financially, but with access to some of the most powerful observatories on Earth. The project primarily uses three major facilities: the Green Bank Telescope in West Virginia, the world's largest fully steerable radio telescope, the Parkes Observatory in Australia, famous for supporting NASA's Apollo missions, and more recently, the Meerkat Array in South Africa, which offers massive data collecting power through its 64 linked dishes. These instruments are tasked with scanning millions of stars across the Milky Way and nearby galaxies, listening for narrow bandwidth radio signals so precise and structured that they would stand out sharply against the background noise of the universe and the messy static of natural sources. What makes Breakthrough Listen unique isn't just its scale, it's also the depth and resolution of its search. It's not simply looking for random beeps or pulses. The project has developed advanced algorithms and artificial intelligence techniques to analyze petabytes of data in search of technosignatures, indicators of artificial origin, such as narrowband emissions, periodic pulses, or signals that drift in frequency in ways that mimic orbital motion or intelligent modulation. Unlike previous efforts, which often focused on short observations of selected targets, Breakthrough Listen spends hundreds of hours scanning the same regions, increasing the odds of catching intermittent or rotating signals. It also observes across a broad frequency range, covering everything from 1 GHz to 12 GHz, a swath of spectrum sometimes referred to as the terrestrial microwave window, which is relatively quiet and ideal for interstellar communication. In addition to targeting specific exoplanet systems known to have potentially habitable planets, the project also engages in wide-field scans of entire regions of the sky. This dual approach, narrow, targeted listening combined with broad, blind surveys, ensures that the project doesn't miss either the obvious or the unexpected. One of the foundational philosophies behind Breakthrough Listen is that absence of evidence is not evidence of absence. The silence we've experienced so far might not reflect a lonely universe, but simply a limited search. Think of it like dipping a cup into the ocean and finding no fish. This doesn't prove the ocean is empty, only that your cup was small. Breakthrough Listen aims to dramatically expand the size of the cup. Over the years, the project has released massive datasets, hundreds of terabytes of raw observations, into the public domain, encouraging citizen scientists, students, and researchers around the globe to participate in the search. This transparency and openness mark a new phase in SETI, one in which the search is not just confined to academic silos, but is shared by humanity. If the first signal ever comes, it will likely be detected, decoded, and understood through collaborative global effort. One of the most remarkable things about Breakthrough Listen is that it also operates in a space of scientific neutrality. It doesn't assume what aliens would do. It simply sets up an extraordinarily powerful system and listens, letting the data speak for itself. In a universe of infinite possibilities, this openness to surprise may be the project's greatest strength. And it doesn't limit itself to radio. The team also explores optical SETI, looking for extremely brief but powerful laser pulses that could serve as interstellar Morse code. These optical beacons, if aimed in our direction, might outshine entire stars for nanoseconds. Telescopes like Lick Observatory's automated planet finder are repurposed to look for such pulses in the visible light spectrum. The project also plans to support and integrate data from future telescopes, including those that will come online in the next decade, like the Square Kilometre Array, SK, which will dwarf today's facilities in sensitivity and sky coverage. When the SK becomes operational, Breakthrough Listen's capabilities will grow exponentially. So far, the project has not discovered any confirmed alien signals. But it has uncovered thousands of intriguing, candidate signals, most of which are eventually traced to human interference, satellites, radar, Earth-based transmitters. However, Each candidate helps refine the process, improve the algorithms, and sharpen our tools for detecting the real thing, should it ever arrive. But the significance of Breakthrough Listen goes beyond discovery. It reflects the deeper, existential ambition of humanity, the desire to know whether our story is singular or shared. It invites us to dream not just about finding life, but about what kind of life we might find. A whisper in the dark could redefine biology, philosophy, and technology all at once. It would upend everything, and yet, it would also make us more at home in the universe. In many ways, the project is a beacon of optimism. It operates on the belief that someone might be trying to reach out, and that by listening patiently, diligently, and with ever-increasing sophistication, we might one day catch their voice. Perhaps it will come as a simple ping from a distant star. Perhaps it will be a pattern, a language, a coded map. Or perhaps just a burst of energy too clean to be natural. Whatever it is, we'll be listening. And if nothing ever comes, if the skies remain silent despite decades of searching, then Breakthrough Listen will still have achieved something profound. It will have charted the cosmic quiet with precision. It will have mapped the vastness and reinforced the preciousness of what we are. It will remind us that even in the absence of an answer, the asking itself has meaning. Because to listen is to hope. Mars has always haunted the human imagination. Long before our robotic emissaries touched down on its dusty surface, it was the red dot in the sky that sparked dreams of alien civilizations, canal-building engineers, and Martian invasions. But as science replaced speculation, the question only grew sharper, more refined, and more compelling: was there ever life on Mars? And perhaps even more intriguing, is there still life there now, hiding beneath the surface or clinging to some unseen niche? What we've learned in the past few decades has transformed Mars from a cold, dead rock to a planet that might once have teemed with life, or at least the potential for it. Today, the case for past or present life on Mars is not built on fantasy but on layers of compelling evidence: water, chemistry, geology, and mysterious bursts of methane. Let's begin with the most crucial ingredient: water. Life as we know it cannot exist without it, and for decades, one of the primary goals of Mars exploration has been to determine whether the red planet once hosted liquid water, and perhaps still does in some form today. Thanks to orbiters, landers, and rovers like Mars Odyssey, Mars Reconnaissance Orbiter, Spirit, Opportunity, Curiosity, and now Perseverance, we know that Mars was once a wet world. There is extensive evidence that rivers, lakes, and even possibly oceans once existed on Mars. Ancient riverbeds snake across its surface, delta formations appear where water once pooled, and mineral deposits, like clay and hydrated salts, only form in the presence of water. Some regions even show signs of catastrophic floods, suggesting that massive outpourings of water reshaped entire landscapes. But it's not just the distant past that holds promise. There's strong evidence that liquid water may still exist beneath Mars's surface, especially near the polar regions. In 2018, radar data from the European Space Agency's Mars Express mission revealed a subsurface lake of briny liquid water beneath the South Polar ice cap. Though it's extremely salty and under tremendous pressure, such water could be a habitable environment for extremophiles, microorganisms that thrive in similar extreme conditions on Earth. Next, we turn to organic molecules, the carbon-based building blocks of life. In 2015, NASA's Curiosity rover made a groundbreaking discovery when it detected complex organic compounds in ancient Martian rocks, dating back over 3 billion years. These molecules are not themselves proof of life, as they can be formed through non-biological processes, but their presence confirms that the ingredients for life existed on Mars for a long time. Further analysis showed that these organics vary seasonally and increase with depth, raising questions about their origin and preservation. Then came one of the most tantalizing Martian mysteries of all, the methane spikes. Methane on Earth is primarily produced by biological sources, such as microbes and decaying organic material, though geological processes like serpentinization can also release it. So when Curiosity detected episodic spikes of methane in the Martian atmosphere, scientists were electrified. These spikes occurred in levels far above the expected background, and intriguingly, they seem to fluctuate with the seasons, hinting at a dynamic process at work. What's most puzzling is the variation in detection across different instruments. While Curiosity on the surface detects occasional bursts of methane, orbiting instruments like the European Trace Gas Orbiter (TGO) have largely come up empty. This discrepancy has sparked numerous theories. Perhaps the methane is rapidly destroyed by unknown chemical processes, or perhaps it's being released in localized plumes that escape satellite detection. But if even a fraction of that methane is biogenic in origin, it would imply the existence of microbial life somewhere underground, life that survives away from radiation, deep within sheltered aquifers. Mars may also offer fossil evidence of life from the past. Some Martian meteorites, like ALH 84001, which was discovered in Antarctica in 1984, have been studied for decades due to their unusual structures that resemble microbial fossils. While the scientific community remains divided on whether these formations are truly biological or the result of abiotic processes, the meteorite brought mainstream attention to the idea that life might once have existed on Mars and left behind a fossil record. Then there's the chemistry. Mars's soil contains perchlorates, salts that lower the freezing point of water and could allow briny liquid to exist even in today's harsh surface environment. Certain regions have also shown evidence of transient water flows, such as recurring slope lineae, dark streaks that appear and disappear with the seasons, potentially caused by salty water trickling down slopes. While controversial, these features hint at the possibility of subsurface liquid brines that might offer refuge to hardy microbes. The newest generation of Mars missions is now explicitly designed to look for signs of life. NASA's Perseverance rover, for instance, is exploring Jezero Crater, a site that was once a lake and has preserved ancient river delta sediments. These sediments are prime targets in the search for biosignatures, subtle chemical or structural indicators that life once existed there. Perseverance is also collecting samples that will be cached for a future Mars sample return mission, a collaboration between NASA and ESA that could finally bring Martian rock back to Earth for high-precision laboratory analysis. That future sample return could be historic. If even a single microfossil, or molecular biosignature, is discovered, it would change everything. It would mean life arose independently on two planets in the same solar system, suggesting the universe may be teeming with life. It would also validate decades of research and ignite a new era of astrobiology. But we must tread carefully. Mars is a complex and chemically active world. Many of the signals we see, organics, methane, brines, can be produced through abiotic means. That's why the scientific community holds itself to a high standard of evidence. After all, the discovery of alien life, even microbial, would be the most profound scientific discovery in human history. Yet even without definitive proof, Mars has already transformed how we think about life in the universe. It has shown that a once lifeless desert can hold secrets beneath its dust, that the search for life is not confined to distant exoplanets, and that the closest answers to our oldest questions may lie just one planet away. In the coming years, new missions, NASA's sample return, China's Mars sample collection plans, and eventually crewed missions by SpaceX and others, may finally crack the mystery. And when that moment comes, when the microscope slides under its lens a tiny fossil or a strand of alien DNA, we will look back at the decades of careful, determined exploration as the steps that led us to one of the most soul-stirring realizations of all, that we were never alone, not even in our own solar system. As astronomers began to study the movement of stars and galaxies more closely, they stumbled upon a puzzle so strange it challenged the very foundations of physics. Galaxies weren't rotating the way they should. The stars at their outer edges were moving far too quickly, defying the predictions made by Newtonian mechanics and Einstein's general relativity. This strange behavior is known as galactic rotation anomalies, a mystery that, to this day, has no fully accepted solution. Most scientists attribute these anomalies to an invisible form of matter, dark matter, believed to make up around 85% of the mass in the universe. This mysterious substance doesn't emit light or radiation, and we can't observe it directly. But its gravitational effects are everywhere. The leading explanation for the flat rotation curves of galaxies is that they are surrounded by massive halos of dark matter, exerting enough gravitational force to keep their stars from flying apart. But what if that's not the only explanation? Some researchers and theorists have proposed alternative possibilities, ones that tread into far more speculative territory. Among the most provocative ideas is the suggestion that some galactic rotation anomalies might not be natural at all, but rather the result of engineered astrophysical phenomena. That is, artificial manipulations of gravity, mass, or motion on a galactic scale, megastructures or technologies constructed by advanced civilizations. To appreciate the scale of such a claim, we need to revisit the Kardashev scale, which categorizes civilizations by their energy usage. A Type 2 civilization would harness the energy of an entire star. A Type 3 civilization, the highest level on the scale, would control energy on the scale of an entire galaxy. If such civilizations exist, their fingerprints might not come in the form of radio signals or laser beams, but rather in massive scale structures and gravitational effects, influences so large they might be hiding in plain sight within our observations of cosmic mechanics. This is where anomalies in galactic rotation become interesting from an astroengineering perspective. Some thinkers propose that the uniform rotation of stars and galaxies, where outer stars orbit just as fast as inner ones, might not simply be a result of dark matter. Instead, they speculate, what if we're observing deliberate gravitational balancing? What if something, or someone, has manipulated mass distributions in ways that mimic the effects we attribute to invisible matter? This idea might seem outlandish, but it's not without precedent in science fiction and theoretical physics. The concept of stellar engines, devices built around stars to move them through space, suggests that it's theoretically possible to manipulate stellar motion. If a Type 3 civilization can move stars, then in principle, it could reorganize the mass of an entire galaxy. And with enough energy and time, perhaps even flatten the galactic rotation curve itself. There are other potential signs. Some galaxies appear to have strange mass distributions, warps, or bends that don't neatly align with standard models of gravitational dynamics. Certain galaxy clusters show unusual accelerations or non-random arrangements, leading a few fringe researchers to speculate whether large-scale intelligence could be involved. And then there are galaxies that seem too well-ordered, whose spiral arms retain their shape longer than expected, or whose stellar population distributions defy expected entropy. Some posit that this might be a sign of galactic-scale maintenance, perhaps by robotic or autonomous systems seeded millions of years ago by advanced civilizations to optimize stellar environments or preserve habitable systems. These ideas are not widely accepted in mainstream astrophysics, and for good reason. The burden of proof for asserting the presence of intelligent engineering on a galactic scale is unimaginably high. But that doesn't mean such ideas are devoid of value. They stretch the boundaries of our thinking and keep us open to the possibility that nature and intelligence may intersect in ways we haven't yet recognized. One of the key concepts in this speculative field is stellar rearrangement, the theoretical idea that a civilization could shift the positions of stars over long periods of time, either to make room for engineered structures like Dyson swarms, or to avoid collisions and optimize habitable zones. Theoretically, if such a process occurred gradually over millions of years, we might not detect sudden changes but instead observe subtle gravitational effects, the very kinds of effects that lead to puzzling rotation anomalies. There's also the notion of mass shielding or lensing. Some theorists suggest that incredibly large-scale structures, like artificial mass lenses or cloaking fields, could bend or obscure gravity in ways that mimic the presence of dark matter. Such constructs would be beyond our engineering capabilities by orders of magnitude, but for a civilization thousands or millions of years ahead of us, such feats might be child's play. Another potential clue comes from our ongoing attempts to map gravitational waves and mass distributions across the cosmos. If we ever observe regions of space where gravity behaves too cleanly, where celestial bodies are arranged with suspicious regularity, it could be a sign of artificial mass manipulation. These would not be like cities on planets but cities of stars, monumental rearrangements visible only when we step back and view entire galaxies as canvases. Skeptics rightly point out that these theories veer far beyond the current evidence, and that there are simpler explanations, like modified gravity theories or baryonic dark matter. But the allure of interpreting cosmic anomalies as possible signs of alien engineering remains powerful, not because we expect it, but because if it's true, it would mean that intelligence has reshaped matter on the largest scale known to science. And if we do someday confirm that galactic rotation anomalies are the signature of astroengineering rather than dark matter, it would fundamentally change our relationship with the cosmos. We would no longer be passive observers of a natural universe, but late arrivals to a playground that someone else has already begun to build. Ultimately, whether these anomalies stem from dark matter, new physics, or advanced intelligence, they remind us that the universe is far more complex and surprising than we imagined. We may look at spinning galaxies and see only elegant spirals of light, but perhaps, behind those curves, there is design. Or perhaps not. But the act of asking, of daring to entertain the unimaginable, is the first step toward discovery. The possibility that Earth once hosted intelligent life long before humanity is a question that cuts deep into both science and imagination. Known as the Silurian hypothesis, this bold idea explores the notion that an advanced civilization might have arisen on our planet millions, even hundreds of millions, of years before humans evolved, leaving behind only subtle traces or none at all. Named partly in jest after a fictional race of intelligent reptiles from the British science fiction series Doctor Who, the Silurian hypothesis is anything but science fiction at its core. It's a rigorous, deeply thought-provoking scientific inquiry into the limits of the geological record, and what evidence of ancient intelligence might actually survive across the eons. First proposed formally by Gavin Schmidt, a NASA climate scientist, and Adam Frank, an astrophysicist, the hypothesis asks a deceptively simple question: if an industrial civilization had existed on Earth millions of years ago, would we be able to detect it today? The answer, it turns out, is far more complicated than it seems. To understand why this is even plausible, we must first recognize that human civilization, everything we've built, has only existed for about 10,000 years, and the industrial age has been here for just over 200. In geological terms, this is a blink of an eye. Most of our physical creations, cities, roads, plastics, and even digital data, are incredibly fragile on a timescale of millions of years. Buildings collapse, metals corrode, organic materials decay. Even concrete breaks down, and unless deliberately protected, most man-made artifacts degrade rapidly when exposed to weather, microbial life, and shifting Earth. Take New York City, for example. If humans disappeared tomorrow, nature would begin reclaiming it in days. Within centuries, vegetation would overtake skyscrapers. In a few thousand years, most structures would collapse entirely. Fast forward 1,000,000 years, and you'd be hard-pressed to find more than chemical shadows in the soil where a massive metropolis once stood. So imagine a civilization that existed 50 million years ago, during the Eocene epoch, or even earlier in the Silurian period, some 400 million years ago, when life was still mainly in the oceans and the first land-based ecosystems were forming. If a sentient species had risen then, perhaps aquatic or amphibious, what would be left of them today? Not much. This is the unsettling crux of the Silurian hypothesis. Absence of evidence is not evidence of absence, especially when it comes to deep time. The Earth is constantly recycling its surface through plate tectonics, erosion, glaciation, volcanism, and biological activity. In less than 100 million years, most of the seafloor is completely recycled. Mountains rise and fall. Continents drift. Only a small fraction of Earth's surface remains geologically stable for longer than 200 million years. So even if an ancient civilization had once flourished, developing cities, machines, perhaps even space travel, much of their evidence would have been obliterated by now. But there may still be indirect clues, and this is where things get interesting. Schmidt and Frank suggest looking for anomalous chemical signatures in the geological record. For instance, our modern industrial activities are leaving behind stratigraphic markers that will be visible for millions of years to come: sharp increases in carbon dioxide, altered nitrogen cycles from agriculture, plastics in sediment layers, and even isotopic signatures from nuclear testing. If similar anomalies occurred millions of years ago, they might point to an earlier civilization. And fascinatingly, there are a few such anomalies in the geological record, though none are currently attributed to intelligent life. One example is the Paleocene-Eocene thermal maximum, PTM, a dramatic global warming event that occurred about 56 million years ago. During this time, global temperatures rose by as much as 8 degrees Celsius 14 degrees Fahrenheit, massive quantities of carbon were released into the atmosphere, and ecosystems around the world were profoundly affected. It's unclear what caused it: massive volcanic eruptions, methane clathrate release, or asteroid impacts are all possible. But it raises the provocative question: could such an event have been driven by industrial activity? Schmidt and Frank don't argue that this is likely. Rather, they propose it as a test case. If there were such an ancient civilization, what kind of geological fingerprint would they leave? And would it resemble this kind of anomaly? They call for a systematic search for unexplained signals in the geological and fossil record: abrupt carbon changes, isotopic anomalies, unusually rapid extinctions, or unexpected concentrations of metals that might be tied to industrial processes. But what about fossils? Wouldn't an intelligent species leave behind skeletons or artifacts? Not necessarily. Fossilization is an incredibly rare process. Most organisms decompose without a trace. Only a minuscule fraction become fossils, and these are typically from environments conducive to rapid burial, like floodplains, lakes, or seabeds. If an ancient intelligent species lived in a forest, or especially if it was aquatic, their remains would likely be lost to time. And even if we did find fossilized remains of an unusual species, recognizing it as intelligent would be extremely difficult without accompanying artifacts, tools, or structural remains. There's also the possibility that an earlier civilization didn't look like us at all. It may have evolved along entirely different biological lines, perhaps reptilian, avian, or even cephalopod-like. Intelligence, after all, is not uniquely tied to human form. We already see rudimentary tool use and problem-solving in birds, dolphins, and octopuses. Who's to say an intelligent, tool-using species didn't evolve and go extinct in the Permian or Jurassic, their legacy erased by mass extinction or tectonic shifts? And finally, we must consider this chilling idea: what if intelligence arises frequently on Earth, but never survives long? Civilizations may rise, flourish, reach a technological peak, and then collapse through war, climate catastrophe, asteroid impact, or some unknown bottleneck. If this has happened before, and will happen again, then human civilization is just one of many brief sparks in the vast timeline of our planet. The Silurian hypothesis isn't about proving that ancient aliens walked the Earth. It's a reminder of how fragile evidence is across deep time, and how little we might know about our planet's true past. It invites us to imagine Earth not as a blank slate that waited 4 billion years for humans, but as a possible cradle for multiple waves of intelligence, each one erased by time. And if intelligence can emerge multiple times on a single planet, that has profound implications for the search for extraterrestrial life. It would mean the galaxy could be littered with civilizations, each rising briefly, only to disappear, leaving behind only mysteries in the dust and stone. Perhaps we are the first. Perhaps we are not. But Earth's silence does not mean it has always been quiet. One of the most captivating possibilities in the search for extraterrestrial intelligence is the notion that a signal from another civilization might not come from a single star or a lone planet, but instead could be part of a synchronized pattern spread across multiple stellar systems. This idea adds a profound twist to SETI research. What if advanced civilizations aren't just trying to be heard, but are intentionally coordinating signals across vast distances to ensure their message is impossible to miss? This line of thinking is known as the study of synchronized signals across stars, and it opens the door to a whole new class of potential alien communication strategies, ones that may be cooperative, strategic, and designed to grab attention through highly deliberate timing. At the core of this hypothesis is the concept of synchronization, multiple signals arriving at Earth from different parts of the sky but at precisely the same time, or according to a repeating pattern that suggests coordination. Such signals would stand out against the cosmic background noise and natural astrophysical phenomena, which tend to be random, isolated, or governed by well-understood physics. If we were to receive multiple, identical signals from separate stars spaced light years apart, and they arrived simultaneously or in a rhythmically repeating interval, that would be extremely difficult to explain as a natural event. But is it even feasible? Given the vast distances between stars, any civilization attempting such a feat would need extraordinary knowledge of galactic geography and timing. They need to account for the light travel time differences, the motion of stars, gravitational lensing, and the precise position of the receiving civilization, us. They'd have to anticipate where we would be, how far we are from each beacon, and when we would be able to observe. In other words, the very act of sending a synchronized signal to us would imply immense technological capability, and perhaps long-term planning. It would suggest that the sender not only has detailed maps of our region of space, but may also have been monitoring our solar system for a long time. It would signal a highly deliberate intent to be discovered. Why would a civilization do this? The answer might lie in optimization. A single message from a distant planet could easily be missed. Earth is spinning, rotating around the sun, and our detectors only scan small fractions of the sky at a time. If a signal arrives when a telescope isn't looking, it's lost. But if multiple signals are sent from different directions and timed to converge, the chances of detection rise dramatically. This is known as a galactic attention-grabbing strategy, a cosmic megaphone where the message is designed not just to be received, but to demand notice. Some researchers theorize that synchronized signals might take the form of pulses or bursts, brief, high-intensity transmissions separated by regular intervals that correspond to mathematical patterns like prime numbers or Fibonacci sequences. Others propose frequency hopping, where multiple signals jump across the radio spectrum at predictable intervals, effectively forming a cosmic beat that intelligent listeners could tune into. In recent years, SETI teams have begun actively analyzing data with this kind of synchronization in mind. Using observatories like the Green Bank Telescope and Breakthrough Listen's massive data archives, researchers apply pattern recognition algorithms and time series analysis tools to hunt for correlations between signals detected in different directions. The hope is that a non-random clustering, whether in timing, structure, or frequency, might emerge, suggesting a deliberate attempt to be heard. One particularly interesting approach is to look for same message, different stars cases, that is, transmissions that are structurally similar, same frequency drift, same duration, same modulation, but originating from separate stars. If two or more stars light up with the same message, that would defy every known natural explanation. This raises the question, how would such a coordinated effort even be possible? After all, stars are separated by tens, hundreds, or thousands of light years. Sending a signal from two such points to arrive at Earth at the same time would require precise knowledge of the distance and timing offsets. That level of synchronization would require planning on a civilizational, or even galactic timescale. It could only be done by a civilization that either 1. Has been broadcasting these signals for thousands or millions of years, and we are only now stepping into their beacon zone, or 2. Has developed a network of autonomous probes or relay stations, possibly self-replicating von Neumann machines, that monitor target regions and coordinate signal timing locally. In the latter case, this would imply not just a civilization, but a technological ecosystem, spread out over many star systems, possibly operating long after the originating species has gone extinct. These probes could be using synchronization as a failsafe, to make sure that if intelligent life ever arises and becomes technologically capable, they won't miss the message. This leads into another mind-bending concept. What if synchronized signals are a form of galactic beacon network, laid down millions of years ago by ancient intelligences as part of a long-term plan to alert future species like us to their existence? Such a network wouldn't need to transmit all the time. It might send out pings at regular galactic intervals, perhaps every few thousand years, waiting for the right conditions to be noticed. And here's a chilling thought: if such a network exists, and we're only now beginning to tune in, then the signals we may receive could be millions of years old. The civilization that sent them may be long gone, leaving behind only its echo and coordinated starlight. But despite the theoretical appeal, there are massive challenges to detecting synchronized signals. Our radio telescopes observe a tiny fraction of the sky at any one time. We would need a global, or even interplanetary array of synchronized detectors, like a distributed telescope network, to continuously monitor wide swaths of the sky for such fleeting and rare alignments. This is one reason why projects like Breakthrough Listen and the Future Square Kilometer Array are so important. They may give us, for the first time, the observational capacity to see patterns across both space and time. And yet, even now, whispers of anomalies occasionally emerge. Strange repeating bursts, narrow-band pulses, unexplained drifts. Most are ultimately traced back to mundane causes, interference, instrumental error, known astrophysical sources. But every so often, one lingers just long enough to provoke debate. Could these be fragments of a larger pattern we're too limited to see? It's a possibility that excites SETI researchers, not because it's likely, but because it's testable. That's the beauty of science. If intelligent civilizations exist and they are trying to be noticed, synchronization across multiple stars might be their clearest fingerprint. And should we one day detect such a pattern, echoes from across the galaxy, perfectly timed, unmistakably intelligent, it would mean we are part of something far greater than ourselves. A conversation not between planets, but across stars. A network older than humanity. A signal meant not just for us, but for anyone who dares to look, to listen, and to understand. While most discussions around alien life focus on detecting signals, atmospheric biosignatures, or signs of technology in real time, there exists a quieter, more speculative branch of inquiry that asks a fundamentally different question: what if the aliens have already been here? Not necessarily in the present, but at any point across cosmic history. This is the foundation of xenoarchaeology, the theoretical and highly speculative field that deals with the potential archaeological study of extraterrestrial civilizations, their artifacts, structures, or technology, whether buried beneath planetary surfaces, drifting through space, or hidden in plain sight. Unlike SETI, which listens for signals, or exoplanet science, which searches for biosignatures in alien atmospheres, xenoarchaeology assumes that intelligent life may have left behind physical evidence that is ancient, silent, and possibly non-functional, but still detectable if we know where, and how, to look. The very idea of alien artifacts might sound like science fiction, but there is solid reasoning behind it. Consider this: humanity has already launched hundreds of spacecraft, some of which are now permanently beyond the solar system. We have left robotic landers on the Moon and Mars, orbiters around Venus, and defunct satellites in Earth's orbit. 1 billion years from now, most of those objects will be gone, but a few, like the Voyager probes, might survive in the emptiness between stars for millions, even billions of years. In this context, it is perfectly reasonable to ask, have other civilizations done the same? If intelligent life is older and more widespread than we are, as some theories suggest, then there's a non-zero chance that they may have already explored or seeded parts of the galaxy, including our solar system, long before humans evolved. If so, we might expect to find relics, ruins, or anomalies, perhaps on airless bodies like the Moon, in the asteroid belt, or even buried on Mars, protected from erosion. One of the most famous thought experiments supporting this idea is the Bracewell probe. Proposed by Ronald Bracewell in 1960, it describes a hypothetical autonomous interstellar spacecraft sent by an alien civilization to explore, monitor, or even communicate with emerging intelligent species. Unlike active beacons, a Bracewell probe would remain dormant until triggered, perhaps by detecting a specific level of radio technology or spaceflight from a nearby planet. In this sense, such a probe could be seen as a time capsule of alien intelligence, waiting silently, hidden in orbit or cloaked among near-Earth asteroids. This raises the question: if such objects exist in our solar system, where should we look? Many researchers suggest we start with the Moon. Because it lacks weather, tectonics, and an atmosphere, the Moon is essentially a preserved fossil of the solar system. Any object placed there could remain intact for millions, perhaps even billions, of years. Even shallow burial under regolith would shield artifacts from radiation and micrometeorites. Some have proposed high-resolution scans of the lunar surface to identify unnatural geometries, rectilinear structures, metallic reflections, or unusual shadows. While none have been confirmed so far, the Moon remains one of the best candidates for xenoarchaeological exploration. Another promising location is Mars, especially now that we have rovers actively exploring its surface. Mars has a more dynamic environment than the Moon, but there are still ancient, stable regions, such as lava tubes and dry lakebeds, where alien artifacts, if they exist, could remain relatively undisturbed. Indeed, a few curious rocks photographed by Mars rovers over the years have sparked speculation, not because they're genuinely alien, but because their strangely geometric shapes occasionally blur the line between geology and design. While all such cases have natural explanations so far, the possibility remains that genuine artifacts might one day be uncovered, especially once human explorers begin full-scale excavation. But perhaps the most intriguing targets lie not on planets, but in space itself. Earth's orbit is cluttered with debris, and our tracking systems already monitor thousands of objects. Some theorists suggest that we should analyze this catalog for non-human anomalies, objects that do not match any known launch history or that follow peculiar orbits inconsistent with natural bodies. Similar surveys are now extending to Earth's Lagrange points and to the asteroid belt, especially the region of co-orbital asteroids known as Trojans, which are gravitationally stable and could harbor long-hidden objects placed there intentionally. In 2020, an asteroid designated 2020 so drew attention for its unusual, Earth-like orbit. Initially thought to be an alien artifact by some, it was eventually confirmed to be a piece of a 1960s-era Centaur rocket booster. Yet the event demonstrated how plausible it is for objects to hide in plain sight, appearing to be natural until we look closely. Xenoarchaeology also explores the possibility of alien artifacts embedded in ancient Earth strata, fossilized machines, strange isotopic signatures, or manufactured alloys with no known terrestrial origin. This echoes the Silurian hypothesis, which raises the possibility that intelligence may have arisen on Earth long before humans. While no such finds have ever been substantiated, the search continues, not for proof of ancient alien visitors per se, but for anything in the geological record that defies known science. Perhaps even more speculative is the idea that alien structures may exist in deep space, too far from any planetary system to be easily detected. These could include derelict megastructures, ancient space stations, or probes no longer transmitting. Advanced civilizations may have built self-replicating machines, or even interstellar arcs that never reach their destination. Some of these structures, if powered down or destroyed, would emit no signals, and would be detectable only through reflected starlight or thermal radiation. Xenoarchaeologists must therefore think like detectives of deep time, sifting through cosmic noise for any signs of deliberate construction, patterns of decay, or unnatural regularity. They often collaborate with SETI researchers, planetary scientists, and even machine learning experts to comb through immense datasets, looking for the needle in a billion light-year haystack. The implications of finding even a single alien artifact are beyond comprehension. It would mean that we are not the first technological species, and that intelligence has left its mark on the galaxy, perhaps many times over. It would also offer direct insights into alien thought, design, and engineering, potentially transforming every field of human science, philosophy, and culture. But perhaps the most sobering aspect of xenoarchaeology is its silence. Despite decades of exploration, we have found no undeniable alien artifacts. Some interpret this as confirmation that we are alone, or at least the first. Others caution that our methods are still too primitive, our instruments too crude, or that we are looking in the wrong places, with the wrong assumptions. After all, any artifacts left behind by a million-year-old civilization may not resemble anything we would recognize. They might not be made of metal or stone, but of exotic materials that have long since disintegrated. Or they may be self-concealing, deliberately hidden to avoid detection by primitive species. They could be encoded in quantum states, or even exist in dimensions or domains of physics we have yet to discover. Still, the possibility remains. Somewhere, out there, a silent probe might drift through the void. A forgotten machine might rest beneath ancient lunar dust. And one day, as our eyes and instruments grow sharper, we may uncover not just signals in the stars, but artifacts in the silence. As we expand our search for extraterrestrial life beyond Earth, we begin to consider environments that are radically different from the familiar. Some of these exoplanets may orbit stars that bombard them with intense ultraviolet radiation or exist without protective atmospheres, exposing their surfaces to harsh cosmic conditions. In these extreme scenarios, traditional biosignatures like oxygen or methane may not be sufficient, or even present. Instead, scientists have started exploring biofluorescence as a novel and potentially visible indicator of life, especially for organisms that may have evolved to glow as a means of survival. Biofluorescence is the phenomenon where organisms absorb high-energy light, such as ultraviolet radiation, and re-emit it as lower-energy visible light, often in striking greens, blues, reds, or purples. On Earth, this adaptation is found in various species including corals, jellyfish, fish, amphibians, and even reptiles. It typically serves as camouflage, communication, or a way to protect against harmful sunlight. But what if this glowing defense mechanism isn't just an earthly quirk? What if it's a universal strategy, a biochemical defense common among life forms on radiation-bathed alien worlds? This idea has sparked growing interest among astrobiologists, particularly in the search for life on planets orbiting red dwarf stars, or M-dwarfs, which are the most common type of star in our galaxy. These stars are smaller and cooler than the Sun, but they tend to produce frequent and intense solar flares, violent bursts of ultraviolet and X-ray radiation that can strip away planetary atmospheres or sterilize planetary surfaces. For life to survive on a planet in such a system, it would need a robust biological mechanism to mitigate this constant radiation onslaught. Enter biofluorescence. On planets with thin atmospheres or little ozone protection, surface-dwelling organisms might evolve fluorescent proteins as a form of natural sunscreen, absorbing harmful UV radiation and re-emitting it in safer wavelengths. Over time, natural selection would favor organisms with more efficient fluorescence, ones capable of neutralizing even the harshest radiation, potentially leading to ecosystems filled with glowing lifeforms. In fact, some researchers speculate that entire biospheres could glow under UV-rich starlight, making fluorescence not just a survival tactic, but a planet-wide signature of life. What makes biofluorescence especially exciting is that, unlike gases or subtle reflectance signatures, it's visually dynamic. Under UV or high-energy light, a fluorescent organism or terrain would light up suddenly, and if such a planet were observed during a stellar flare event, telescopes might catch the entire surface brightening briefly with colored light, a potential flash of unmistakable biological activity. Astrobiologists have proposed targeting these flare events on nearby M-dwarf exoplanets using sensitive spectrographs and optical telescopes. The logic is elegant. If we monitor a planet during a UV flare from its star and then detect a spike in visible fluorescence, we may be observing real-time biological response to radiation, an alien version of coral glowing under black light. Some Earth organisms exhibit resonant fluorescence, which activates almost instantaneously when exposed to UV light. Others show delayed fluorescence, continuing to glow even after the initial energy source has vanished. Both types could theoretically occur on alien planets, and either would produce distinct spectral signals detectable from light years away, especially when instruments like the James Webb Space Telescope, JWST, or upcoming LUVOIR and HabEx missions are trained on them. In fact, laboratory simulations have already begun to test this. Scientists have exposed known Earth biochemicals, particularly GFPs, green fluorescent proteins, and similar compounds, to simulated exoplanet conditions, studying how their emissions might appear from great distances. The results suggest that fluorescence signatures can be isolated spectrally, meaning telescopes could, in principle, distinguish them from non-biological sources like mineral reflections or star spot flickers. This form of detection, looking for time-variable fluorescence during flare windows would add a powerful tool to our planetary reconnaissance. Instead of relying on static features, we could observe how a planet reacts dynamically to its star, catching it in the act of adaptation, survival, or communication. Even more compelling is the idea that biofluorescence might not just be defensive. It could be a form of signaling or species recognition, an evolutionary path leading to bioluminescent cultures or ecosystems that use color pulses the way we use language. On high-radiation worlds, life might glow constantly, not just to survive, but to thrive, to find mates, or to interact with its environment. Imagine for a moment a jungle on an alien world, bathed in darkness, suddenly coming alive with color as a solar flare hits the planet. Trees and foliage pulsing in coordinated hues. Predators glowing in infrared, while prey shifts its glow to ultraviolet. Skybound plankton illuminating entire oceans. Entire biomes pulsing in electromagnetic rhythms. If such a world exists, its light would betray it. That flash of biofluorescent response during a flare would stand out like a neon signature in the black sea of space. And it wouldn't just tell us that life exists, it might even offer a glimpse into how alien life lives, interacts, and evolves. There's also a more technical reason for the excitement around biofluorescence as a life marker. It bypasses some of the ambiguity of gas-based biosignatures. While oxygen, methane, or ammonia in a planetary atmosphere can suggest life, they can also be produced by volcanic or chemical processes. But time-variable fluorescence, especially if it follows a flare event or correlates with UV light cycles, would be much harder to explain without biological context. Critically, no known non-biological process on a planetary scale would produce delayed, wavelength-shifted emissions in response to UV radiation with the same precision or pattern that fluorescence would. This makes it one of the few potentially unambiguous biosignatures we can hope to detect across interstellar distances. The challenges, of course, are steep. The signal would be faint. The windows of detection would be brief. It would require coordinated monitoring, precision spectroscopy, and probably a bit of luck. But the payoff, detecting alien fluorescence, would be monumental. It's a poetic irony. The universe is mostly dark, quiet, and cold. But perhaps the very life forms we seek are those that learn to glow against that darkness, reflecting their starlight back not with silence, but with color. Somewhere out there, perhaps under a red dwarf sun, a glowing rainforest pulses with ultraviolet defiance. And perhaps, one day, we'll see that pulse across the light years, like a beacon of biochemical resilience, and know, without doubt, that we are not alone. In the vast theater of the cosmos, with its endless stage of stars and countless unseen curtains of dust, there lies a truth so overwhelmingly supported by numbers that it feels less like speculation and more like quiet inevitability. We are almost certainly not alone. This conclusion doesn't come from wishful thinking or blurry photographs. It comes from pure mathematics. Cold and personal, in different numbers that tell a story of astronomical scale and the statistical impossibility of solitude. Let's begin with the backdrop. Current estimates suggest that there are over 2 trillion galaxies in the observable universe. That's a number so large it defies comprehension. Our own galaxy, the Milky Way, is home to about 100 to 400 billion stars, and recent exoplanet surveys indicate that nearly every star hosts at least one planet, with many having multiple. That means the Milky Way alone contains well over 100 billion planets, and possibly as many as 1 trillion if we include moons and other bodies capable of hosting life. Now expand that across the cosmos. Multiply that figure by 2 trillion galaxies. You're left with a staggering total, more than 10 superscript 2 planets in the observable universe. That's 1 septillion worlds. Even if only a minuscule fraction of those planets are in the so-called habitable zone, where liquid water could exist, say, 1 in a million, you're still left with over 1 quintillion potentially habitable planets. And yet, in all of this, we've only confirmed life on one world, Earth. So why does this create such a paradox? Because if you assign even the smallest probability to life arising on a suitable planet, say, 1 in a billion, The sheer number of planets means that life should have arisen not just once, but millions, even billions of times across the universe. The famous Drake equation, formulated by astronomer Frank Drake in 1961, tries to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction of those that develop life, the fraction of life that becomes intelligent, and how long such civilizations might transmit signals into space. Even with conservative estimates, the Drake equation almost always yields a number greater than 0. If you give the emergence of intelligent life even a modest chance, say, 1 in a billion, then across trillions of opportunities, it becomes almost inevitable. This leads us into deep philosophical waters. If the probability is so high, if life is likely, then where is everybody? That's the Fermi Paradox, but the statistical side of the paradox is what magnifies its weight. The numbers are screaming. They must be out there. And yet, we haven't heard a whisper. But that's where our understanding of statistics gives us perspective. Because probability doesn't mean certainty. It means likelihood. And likelihood doesn't guarantee detection, especially given how short our listening window has been. Humanity has only been broadcasting radio waves for about 120 years. We've only had sensitive listening equipment for a few decades. We've only scanned a tiny fraction of the sky at any useful resolution. Imagine you had a massive ocean, spanning the entire planet, and you scooped up a single thimble of water. If you didn't find a fish in that thimble, would you declare the ocean empty? That's where we are with the search for alien life. Our thimble is still suspended above the waves. What makes the statistical argument even more compelling is that life on Earth arose extremely quickly once conditions were stable. Our planet cooled and formed oceans about 4.3 billion years ago, and the first signs of life, simple microorganisms, appear in the fossil record by 3.8 to 4.0 billion years ago. In the cosmic blink of an eye, life was already thriving in Earth's seas. This suggests that, given the right conditions, life emerges easily. It doesn't appear to be a fragile fluke, it may be a robust response to environmental chemistry. And once life exists, it begins to adapt, diversify, and grow in complexity. Intelligent life, of course, is a longer and more unpredictable path. Evolution doesn't guarantee the emergence of brains, technology, or civilizations. But again, the numbers are staggering. If even 1 in a trillion planets develops technological intelligence, that still leaves billions of civilizations spread across cosmic time. And it's not just about now. We often forget that the universe is 13.8 billion years old, while humans have been around for a mere 300,000 years, and modern technology for only about 100. Civilizations could have come and gone millions of years before us. Their traces, radio signals, artifacts, megastructures, might be long gone, faded into entropy, scattered as dust across time. Statistically speaking, we could be late to the party. Or early. Or in a quiet intermission between galactic civilizations. The numbers support all of these possibilities. Furthermore, life might not resemble anything we expect. We base our assumptions on carbon-based chemistry and water, because that's what we know. But statistical models of molecular complexity suggest that alternative biochemistries, perhaps silicon-based, ammonia solvent, or entirely exotic forms, may also emerge given different conditions. The universe doesn't owe us familiarity. Even if we limit our definition of life to Earth-like organisms in Earth-like environments, the number of potential worlds is so vast that it practically guarantees life elsewhere. And yet, the silence remains. This forces us to consider our own limitations, of perception, of expectation, and of technology. We may be listening on the wrong frequencies, interpreting signals as noise, or looking for civilizations that no longer exist. We might miss alien life because it doesn't want to be found, or because it communicates in ways we can't yet detect, using neutrinos, quantum entanglement, gravitational waves, or methods beyond current physics. Some scientists propose that the statistical certainty of life should shift our focus from if to how and where to look. That's why searches for biosignatures on exoplanets, technosignatures in starlight, and xenoarchaeological anomalies are all expanding. We no longer question whether life is out there, we question how we can prove it. In this sense, the statistical impossibility of solitude isn't a conclusion. It's a guidepost. It pushes us forward, challenges our assumptions, and reminds us that our place in the universe is still being written. Because if life is abundant, then the universe is a living, breathing entity of minds and stories and civilizations, most of them lost, some still thriving, and many yet to be discovered. We are not the exception. We are the evidence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.